Well, he's one of the old ones. Amaya, you're the first new student we've had here. Gerald's been here before. Uh, he was in 111. Yes, and well, we haven't. I haven't been on. I've been on the Bessemer campus twice since we shut down in March, and I am trying to think. I don't think I've been on Birmingham campus back, but my main office is on Bessemer, um, and we'll be back on campus either this term or next term as I'm hauling materials back to campus, turning in keys, doing that kind of stuff. So I'll be going to both campuses. But all right, I'm going to see if any students are trying to log in to Blackboard Collaborate. I've never done Collaborate. Have I take it one of you three probably have, haven't you? Do I do I just click on this where it says join session? Can you see what I'm where my finger is pointing? Is that okay? Let's see if anyone's there. It says course room. I have no idea what that means. Click on that. Okay. Okay. And will I see if any other students are here? Okay. Okay. Well, that's what I was guessing. Um, so, wait, here's somebody. Daniel Ruiz. Okay. Hello, Daniel. Can you hear me yet? I don't know if I can do collaborate and. All right. He's in, but he looks like he's in on Zoom now. Oh, he maybe is. So I'm going to get out of collaborate. Okay. And here comes. Uh, okay. Daniel Ruiz. Daniel, what do you go by? Okay. I'm going to I'm going to get out of this. How do I get out of this? Okay. Is this the X for collaborate? I hope so. Okay. I want to get out of collaborate and back to Zoom. Okay, I'm going to move y'all out of the way so I can see what's here. Start recording. Um, no. How do I get out of this? Three lines? Yeah, I see them. And do what? I open it. I want to end it. Oh, leave session. Okay, got it. Thank you. Okay. I want to skip. I want to get out of this thing. Okay. Close the browser window. Where do I do that? Okay, up there. Yuck. I want that open for Zoom, but it's still open. Good deal. Okay. Now, I'm going to move y'all back where you were for now. I'll probably move you around some. And let me see who we got here. Um, Rodrigo Soriano. Okay, got it. Are you dropping this Santana now part, or just how are you doing that? Okay, what do you like to go by? Rodrigo? Do you want both names? What? Rodrigo. Okay, I'll circle that. Okay. And how about it, Daniel? What do you go by? Daniel Ruiz. Daniel? Okay, or Daniel, sir. Okay, I got it. Never mind. Okay. There you are. All right, we got a big gathering right in the middle of the class here. And we got two at the very top. Whoa. Yeah, two at the very top and three in the middle for only 5 students. Ooh, okay. Pretty low attendance so far. Did any one of you try to go to Blackboard Collaborate first? Okay. I just went out there and someone who was familiar with it told me no one was there. So what I think we'll do is go on and start the class. Actually, it has already started. I'm going to minimize this. You probably couldn't see it anyway. Where we are now is this is the Physical Science 112, Physical Science 2 with lab, Blackboard Ultra. I guess you'd say it the home page for our class. They don't. It's not what they call it. It's the content page, course content. That's what it says here. Okay, just wanted to go over a couple things with you. Obviously, you found the announcement because you're here. Okay. Oh, and by the way, let me also say this. I am recording the class. I don't know if you can see the little red dot in the lower left corner. It has 620, 621, 622 counting down. That's how long I've been recording. And this will be after the end of class, and that'll be a long time from now. At the end of class, I will end the recording, and then I'll save it to a YouTube video. And then the YouTube video, when it gets uploaded, and it's going to take a while because this is a 4.5-hour class, so it'll probably be tomorrow morning before I'll be able to post it on a playlist that then you can access, and I'll show you how to access that in just a bit. So that's what's going on so far. Now y'all probably can't see your names over on the corner of the page, but if you do watch the videos, you will see them. So I'm going to move y'all to the top of the page for right now, and let's just talk about Blackboard. Now I guess most of you have had courses in Blackboard Ultra, right? I assume so. Okay. Here is, it says start here, so I'm going to click on that. And it talks about navigating the course and online learning tips. This is, from what I can gather, mostly for online classes, not for the virtual classes. But I left it on here just because the dean put it here and she said, I don't know. So anyway, it does have here the course syllabus. Now, just a couple of things. If you had noticed, and you probably already know this, that start here, I opened it over here. And here's the reason. See, it underlines when you put your cursor on it, but there's no icon here. So therefore, it's not going to open clicking here. You have to come to the right-hand side and click on the arrow. Now it opens. Okay? And what it said before, it says start here to get to know your online course. I changed that to virtual course. Okay? And it says be sure to complete your course syllabus agreement, and it went into all sorts of things of how this is how your first week's attendance is counted and you have to do it. Well, that's for online classes. Now, you do want to do the course syllabus agreement, and we'll talk about that when we get there. Okay? And then the same thing here for the navigating the course online learning tips. I left it there just in case there's anything that you find useful. But here's where I think you really should begin, or that's where I began. The course syllabus. Now it's going to show up in several places, but here's where it is. And well, maybe just this one place. Notice it does have an icon here. It does underline, so you can click on this and that will open up. Okay? And then here are the instructions for you to read the syllabus, and then they go into all sorts of gory detail on how to do the course syllabus agreement. Again, that's mostly for online courses, but if you want to do that and send it to me, you certainly can. Okay? However, I want you to open the syllabus, and here you'll see, here you have an icon, but it doesn't underline when you put the cursor on top of it. That means you have to open it through the 3 dots over here. And they call these 3 dots an elliptical, which is a weird phrase because it has nothing elliptical about it that I can tell, because that's a shape in mathematics. So I don't know why they call it that, but if you click on that, it says download of original file. If I were to click on that, then it shows up in the lower left corner here, and you'll watch it downloading. When it quits downloading, you can click on it and open it up. I've already got it open, so I don't want to download it again. So I'm going to get out of that, and I'm going to now open the syllabus. And that will be right here. Okay. And can you see the syllabus now? Yeah, no, the screen sharing stopped, so I'm going to have to do a new share and get the syllabus in there. And there it is. Okay, now you can see it, right? Okay, Daniel, you're in the way. I'm going to move you over to the right again. Okay. Oh, and here comes Brianna. Okay, now Brianna was in 111 also, so she's an old hat to this kind of stuff. Brianna Page. Now, there's nothing on my class list that indicates majors. And I'm just going to make a guess here. Are any of you automotive? Oh, here comes Jacob. And see which Jacob this is. Jacob Walker, who was in my class, I think in the summertime maybe. Okay, let's get him here. Did you get me, Mr. Powell? And who is that? Brianna. Yes, I got you when I was letting you in. I marked you then. And you go by Brianna, right? Mm-hmm. All right, got it. Okay. Oh, I see. No problem. You're here. That's the important thing. And that's Jacob, right? Yes, sir. Okay. Now, are you the Jacob that was in my class last summer? Yes, sir. Okay, good. I thought you were, but the name was, I thought exactly the same, but I've actually run into more than one people with the same name before, so I wanted to make sure I wasn't making a bad assumption there. So you're, now, for you, Jacob, things are a little different this time because they're making us use a template in Blackboard that's way more complicated than how we used to do it. Maybe y'all like it. If you do, fine, we got it. Another thing that's new is the syllabus. They came out with a new, basically a format for that. So that's what we're looking at right now, and that's what we're going over right now. This is physical science. Oh, and by the way, I was going to ask this question. Are any of you automotive majors? I forgot to mark Gerald's name. You still go by Gerald, right? Gerald? Okay. I'm a social work major. Okay. But none of you are automotive majors? Yes, sir. Oh, you are? Who is this now? Daniel. Daniel. Okay. Do you know if any of your classmates are going to be joining us? Oh, Rodrigo is also. What fantastic. Okay. How about any others? Do you know? Okay. The reason I asked that, if we were all non-automotive majors, now let me make sure my assumption's right. Y'all have a class that ends at 3 o'clock. Is that right? Automotive majors? Repeat that. Sorry, my volume went down. Okay. Y'all, the automotive students have a class that goes up until 3 o'clock, right? Yes, sir. Okay, good. Okay. So we're going to keep things like they are. I was going to say, if none of you are automotive majors, then if you wanted to move the class earlier, we probably could arrange that. But if any of you were automotive majors, I didn't think we could. They're wonderful folks. Okay, okay. And who is he? His name is Rucker Lohman. Okay, last name Lohman. Yeah, Rucker Lohman. I see him. Okay. Now, if you'll pass this word along to him, we'll get there in just a minute. If he can't make it either today or Thursday to class, he's got to turn in his syllabus agreement page. Absolutely has to. The rest of you, we want everybody to do that, but anyone who can't be present today. Now, if the rest of you know anyone else who's in the class, but for some reason they're not going to be here this week, they've got to, absolutely have to, turn in their uh, their syllabus agreement. And we're going to get to that page in a little bit, okay? But I wanted, especially if you knew somebody else who's not here, and I'm going to give a little more time before to let more people show up, and by the end of class I'll read off the names just in case any of you recognize these folks. And this is another change that's different from the summer. The summer we weren't doing this. Since summer we have gone to the banner system. The banner system supposedly kicks out students who haven't attended the first day of class. Now here we have HP coming in, and I don't know who HP is. Does anyone? Yes.
I'm gonna have to leave for 1 second, but I am coming back. I'm having to pick up some medication for my aunt.
Okay. And this is Brianna talking?
Yes, ma'am.
Okay, good. Yeah, well, just hopefully you'll pop up and I'll let you back in.
Okay.
Okay. I'm still waiting to hear from HP. Who is?
I think Valerie. I'm sorry.
Okay, Valerie Winston?
Yes, ma'am.
Welcome back.
I'm
Okay.
good. How are you?
Good, thank you.
Good.
Valerie was a star student this summer. Okay. Uh, I,
Sorry I was late.
I think it was summer, or was it last spring?
Spring.
It was spring. Okay. All right. I think a few of your classmates was Jacob. Was it you in the spring or summer? Summer. Okay. Uh,
You were in the chime in. I'm sorry. I might got off.
okay. Leon Whitney was either spring or summer. I don't remember which. I think he was summer. Um, Thomas Habrowski, I think, was summer. And Diana Patino was here first mini term. So she knows how to get here. Those are the names I recognize. So if you are still in touch with any of those folks and they don't show up this week, tell them they've got to, absolutely have to submit their student course, their um, syllabus agreement. We'll get to that in a little bit. Okay, so here's the syllabus. This is the new ACCS format for it. They didn't come out with this for physical science yet, but I went on and adjusted it for this. We are in Physical Science 112, Physical Science 2, a 4 semester hour course that will be meeting a lot more than 4 hours, closer to 5 hours a week, because it's a mini term course. I'm sorry, 9 hours a week. Okay, no, yeah, that's right. 4.5 hours, 2 days a week. This course provides the non-technical student, though some of you are technical students, with an introduction to the basic principles of chemistry and physics. Now that's the course description that the state came up with a few years ago. We can't change that. We're actually teaching the course physics and chemistry because that's how the book presents it. So we'll be doing physics first and then chemistry at the end. Laboratory is required. We will have lab, not every class, but we'll have a lab period every class, but we may not have a lab to do every class. But we're going to have them more often than once a week. So some weeks we'll have one, some we'll have two. More often, probably two. Today we won't have a lab. Actually, what we're doing now is more like the lab, and then the last part of the class will be more like a class. So okay, prerequisite. As far as I know, no prerequisite is required. I do suggest that you have at least Math 098 under your belt. If you don't, I hope you did pretty well in math in high school, because we will be doing quite a bit of calculations in this class. The Physical Science 1 had very few calculations. Physical Science 2 has quite a few more. The book, for those who were here last time, and even those who weren't, is this one, Bill Tillery. I'll show you what the official book looks like. It's heavy, so I'm not going to hold it long. It's Physical Science by Bill W. Tillery. It's the 11th edition. It's a McGraw-Hill book. It's a pretty thick book. However, if you don't want to spend the money on the thick book, the bookstore on the Bessemer campus. Now, I believe it was Amaya says she's a Birmingham student. They don't have this book on the Birmingham campus bookstore, but they do on the Bessemer bookstore. And if you can run out there, if you want to pick it up. Oh, whoa, whoa, here's Brianna coming back. Boy, that didn't take her long, did it? Okay. Um, if you can run out to the Bessemer bookstore, you can get just the chapters we're covering. They call that a customized edition. It's the same material, but it's only the 6 chapters we'll be covering, bound in one book, much thinner, much easier to handle, and you can do that. You can also, you don't have to buy your book from the bookstore if you can get it from another student, if you can get it at some of the things like Amazon or some of the other textbook places.
It's not Cengage.
It's not a Cengage book. No, it's not. This is a McGraw-Hill book. Okay, so it's
Okay,
not
so I have
Cengage.
Connect. So, but it's
Oh
free.
yes, if you have
It's
Connect,
from my economics class. So,
uh,
will I be able to use that for that too?
I don't know much about Connect except that it is a McGraw-Hill product. So if it will let you do it, yeah. If it's anything like Cengage Unlimited, it should let you do it. But I can't say that for sure because I'm not familiar with. I know what Connect is, but I don't know how they do the book part of it. Okay, so this is a 11th edition. If you can only find an earlier edition, the physical science hasn't changed. What will change are some of the page numbers and some of the pictures and things like this, but by and large, the subject matter is the same. In fact, the PowerPoints we're going to be using are from an earlier edition because they didn't send PowerPoints for this edition. Okay, I can probably get them through Connect, but I've never bothered to learn enough about Connect to do it. Okay, now students are expected to bring the textbook, paper, and pencil to class, wherever you are, home or wherever, every class meeting because we will be working problems. Way more than we did in Physical Science 111 for those of you who had that class. The problems are a big part of both physics and chemistry. Okay, so be sure to have paper and pencil on hand. Calculators certainly are permitted for the course. Okay, and that's why I was saying some math is important for the course, so be sure you have some. Here are the course objectives, and I can't get to them because y'all are in the way, so I'm going to have to move y'all again. And I think I've got you out of the way, but I don't see my scroll bar. Okay, so maybe what I have to do is just, I'm going to have to scroll down this way. Okay, that went a little too far. Oh, there it is. It finally popped up. It was hiding. Okay. All right, let's get back to course objectives. Okay, there was what we did the test book. Here's course objectives. By the end of the course, students should be able to, number one, demonstrate knowledge of the basic principles of science. If you've got your book already, or even if you don't, that's basically chapter one. It's sort of a nebulous little chapter they have at the front of a lot of science books. That's what we're going to deal with there. Number two, describe and measure motion. I should have a comma in there. Identify the relationships between force, mass, and changes in motion. Okay, that's the beginning of that is chapter 2. Number 3, define work, power, and the various forms of energy and how it flows and how they relate one to another. Work, power, energy, and so forth. That's chapter 3. Okay? Demonstrate the relationships between heat, temperature, and the motion and position of molecules. That's chapter 4. Okay? Identify how electric and magnetic fields interact and produce forces. That's chapter 6. We skipped chapter 5, and if you buy the little book in the Bessemer bookstore, there will not be a chapter 5 in it. It goes from 4 to 6. Don't think you're being gypped. We're not doing that. The chapter 5 in that book, or in my book, was vibrations and sound. And it was a great chapter, but I found I never could finish everything we needed if I covered that. So I left off that one. Okay?
You skipping chapter 5?
Skipping chapter 5. So if you have the book, we're skipping chapter 5. Okay?
So just one, two, three, four, and 6.
Well, that's not all. We'll get there. Okay? Um, that's number 5 here is chapter 6. Okay. Number 6 here, demonstrate an understanding of the development of the model of an atom. Okay. Now that came from, that's chapter 8. We're skipping chapter 7 too. Chapter 7 in the big book was light. And again, a great chapter, fantastic chapter, but you see, this book is supposed to be physics and chemistry. And if I did all 7 of those chapters, I wouldn't have time to do any chemistry at all. So that's why we skipped chapter 7 and moved to chapter 8, because this is basically the chemistry chapter we're going to do. But it sets up basically a lot of what you need to know in chemistry to go further if you choose to do so. Another objective is to write a library internet-based, I shouldn't have a slash there, I've got to go back and change this, research-based, internet-based research paper. Okay? Everybody is required to do a research paper. Those who have been in my classes before, you know this. Those who haven't, welcome to Charles Fowlerville. Okay, you will be writing a paper. Not an extensive paper, and we'll go over that a little bit more later today, but it's going to be a research paper, and we'll talk about that later. And this is more when you're in class, but it actually works here too. Work together in groups to solve laboratory assignments. Okay? The labs we'll be doing, we're going to do as much as we can together as one big group. Okay? And then there will be some times when you'll have to write up and work up some additional things as on your own, and then you're certainly welcome and encouraged to work with each other. So share email addresses, Zoom, Skype, whatever you want to do to interact with each other there. All right, so that's the course objectives. Here are the course outline of topics, and that goes right along with what we were discussing before. I'm going to try to leave as much of this on here as possible. Okay, the nature of science, then again, that's number 1 up here, basic principles of science. So the nature of science, that's going to be our first topic. Number 2 up here was talking about motion. There we have motion number 2 here. But also in number 2 up here, we talked about forces. So that's another required topic, forces. The laws of motion, that's also in chapter 2. Okay. Then in chapter 3, work, power, and energy. Those are all mentioned in chapter 3 here, and they're covered in chapter 3 in the book. Chapter 4, heat, temperature, and the motion and position of molecules. There, and this I'm going to have to leave that up top, heat, temperature. Okay, I didn't put, but the molecular theory, kinetic molecular theory, or that's covered too. Okay, then chapter 6, skipping 5, chapter 6, electricity and magnetic fields, how they interact and produce forces. That's electricity is number 10 down here, and number 11 is magnetism. And then your chapter 8 here, which was demonstrate understanding development of the model of an atom, that's chapter 12. That's item 12 down here. Now, was that me, or is someone else trying to come in the course? No, but we have 8 students here. Let me check. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, got everybody. Sometimes I miss, especially when you can't see it, but all your names are up here at the top. That's where Zoom sends a message that someone's trying to enter the course, and if I've got your names up there, I can't always see it. So I'm going to move them in a little bit. Okay, so there, number 12 is model of an atom. That's chapter 8. Periodic table, also chapter 8. Okay. Other topics, waves and sound, that would have been chapter 5. We probably won't get to it. And that shouldn't be lighty, that should be light. Okay, I've got some corrections to make here. I was doing this late last night, and I obviously wasn't proofing very well. Okay, now evaluation and assessment. Okay, Now, all they ask for is this: grades will be given based on A's or 90s, B's or 80s, C's or 70s, D's or 60s, don't go there, F's are below 60, don't go there. Okay? That's what they want here. Let me give you an idea, and here somebody is trying to come in. Let me see if I can get who they are. Rucker is here, so he did show up. Okay. And does he go by Rucker? Rucker, can you hear me yet? No, he's still, well, you can? Okay. What do you go by? Do you go by Rucker or something else?
I go by Rucker.
Rucker, okay. I like to circle what you go by, so if I'm trying to call you down, no, I'm sorry, to just so I'm calling you by what you want to go by. All right, welcome to the class. We've been talking about the syllabus, and this I'll show you where we are on the Blackboard Ultra page when we go back to that page. I was just getting ready to talk about how I evaluate and assess what you're doing, how we come up with these grades. Okay, now you've already heard me say everyone will do a research paper. The research paper counts as a test score that cannot be dropped. Okay, so the research paper is required, counts as a test score. Okay, every chapter we do, 1, 2, 3, 4, 6, and 8, every chapter will have at least one lab. Chapter 1 has only one lab. Chapter 2 on motion has, I think, at least 3 labs. Here's the problem. The last time I taught this course, we were back on campus, and some of the labs that were done on campus can't be easily done in a virtual setting. So I've had to rework the labs. Like the lab for chapter 1, I reworked last night. That was the other thing I was doing besides the syllabus. I had to come up with a whole new lab for chapter 1, because the one we did before, you had to be in a laboratory and do the stuff there. We couldn't do that one, so I came up with a new lab. It uses something called Lab Simulations. It's an outfit out of Colorado, I think Colorado State or University of Colorado, somewhere there, out of Boulder, and they developed these labs, and they're pretty good. Okay, I've got the first one done. When we get to the motion part, I've still got to come out with ways to do those. We did some last spring, but they were pretty pathetic. Okay, I've got to come up with some better. Later in the term, I got a lot better at it, but the first ones we didn't know we'd be leaving campus. Suddenly we left campus. I couldn't do the labs that we would have done on campus, so I had to all of a sudden come up with labs, and that was my first, not my first exposure, but my first major exposure to those lab simulations. So we'll be doing those. I'll be working on getting those put together. Now, I'll warn you right now, some of you may not be able to see all the labs in person. That's why we work them in class together, because I'll make sure I can pull them up, and then since I'm recording the classes, putting on YouTube videos, you can go into the YouTube video and watch us do the lab, even if you can't pull the labs up yourself. It seems like that some labs require a certain Java script or something like this that not everybody has on their computers, and especially if you're only on a cell phone, that's going to be really hard to do. So I'll put it out there so you can follow along and do the labs from the YouTube video. That's why I'll do them all basically in class. There are a couple, for instance, not the last lab, the chemistry lab, will come right out of the book, and that one you'll be able to do right out of the book. Now, if you don't have a book, that's going to be tougher for you. So that's when it's a good idea to get in touch with some other student who does have a book, and maybe y'all can share information like that safely. Okay. So anyway, the labs. Chapter 1 has one lab. Chapter 2 has at least 3 labs. Chapter 3, the work lab work chapter or energy chapter that has, I think, 3 labs. The heat and temperature, if I can come up with them, that will probably have 3 labs. Electricity and magnetism, possibly up to 3 labs for that one. And then the chemistry chapter, 1 lab. So that would be 1 plus 3 would be 4, plus 3 would be 7, plus 3 would be 10. Let me see. 3, yeah, yes, 6, 9, 12, up to 14 labs. We have 16 meeting days. We may not have 14 labs, but we'll have a bunch just about every day. What's your question? Was there a question?
I have one.
Okay, what's that?
I know I emailed you. I know I emailed you about the I probably should have asked earlier. I emailed you about the syllabus and like the syllabus agreement, like the little thing.
Right.
And I went on there. I see that we're going over the syllabus now, but it wasn't on Blackboard. And also like the agreement thing, where like the way they have it set up, like as a test, sort of kind of like the agreement, like it wouldn't let me. It was just like I have zero attempts.
Okay.
Is that something that you have to fix?
Are you talking about this term or last term?
No, this term.
Okay,
It says
this mini term.
syllabus agreement for physical science.
Okay, for physical science 2, 112. Okay, we haven't even gone over the syllabus yet, so I saw that 4 people had done the syllabus agreement and I hadn't even posted the syllabus yet. I don't know how they did it.
I didn't even have the chance to do that because it says that you have zero attempts. So I figured since the syllabus wasn't on there, you didn't open up the agreement thing yet.
Okay, well, I don't know how they do it. What you're running into is a Blackboard issue. I will see if when I go out there if they have some ways for me to change the attempts. They've got to, but I don't know how to do that. That is one of these stupid little idiosyncrasies that Blackboard has. I don't ever put how many attempts there. It puts them in there. I don't ever put due dates in there. It puts them in there. If I catch them, then I'll change them. But I'll have to look for that when I go back and check things. I didn't know they gave you no attempts to do it. But 4 people did it. How they did it, I don't know. Okay. But I saw that when I put the syllabus out there, I 4 people had already done the agreement page and I hadn't even posted the syllabus yet. I thought, yeah, they really read it carefully, didn't they? Okay, if it's one of you, that's fine. I understand, but you had to do it, but it's fine.
Mr. Fowler, this is Valerie Winston. I
Right.
actually printed mine off like early this morning, about 6 or 7 o'clock,
Okay. Yeah. I,
and did mine this morning.
yeah. I put it out there yesterday, and when I put it out there yesterday, there were 4 people who had already done agreements on it before I put it out there. So I thought, well, how in the world? But that's fine. You got your agreement page in, so that's fine. So Valerie, you were able to do it, and it had at least one attempt or something like that. So Brianna, you should be able. Again, that's something.
I can go check again, but like when I did it, it was like you have zero attempts. Your grade is 0 out of 0.
Well, now that's all you're gonna get. There is no,
And
there are no points. Yeah, right.
I didn't have an attempt to like go and like submit it
Okay.
yet.
Okay.
Send me one.
Okay, I'll look into that and see what it is. If you get it to me, you'll get credit for it. Okay, however you
When
can
do you
manage to.
need to establish our attendance for this week?
Okay, that's for people who aren't here in class. Y'all are here in class. You've already established your attendance. And that's why I was saying if you know anybody on the list and before the day's over with, I'll go through all the people who are missing. And that's why I called some of them because I thought some of you might know Thomas from earlier, Diana from earlier, um, Leon from earlier. Those are the only names I recognize here. If you know them, be sure to let them know to get their uh, 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 whatever you call that agreement syllabus agreement page in, because if they aren't here for one of these 2 classes today or Thursday, that's the only way they can get their attendance verified. But you are here, your attendance is now verified. It hasn't yet, but it will be. because you have attended a class. For those who haven't attended, that's the only way they have to say, yes, I'm going to stay with the course. Okay. And that's a function of Banner. Banner is introduced that. We didn't used to have to fiddle with that. So, Valerie, if that sounds new to you, that's what, when we went to Banner this fall, that's that. But you've probably been in other classes you had that too.
Yes, correct.
All right. Now, attendance. Okay.
So, and
Yes.
question: how often do you post attendance?
I'm required to do attendance every day.
Okay.
Yeah, they say we have to. And I post it on Blackboard, and now here's another stupid thing that Blackboard does. It gives you some sort of a grade. There is no grade for attendance. We're not allowed to give a grade for attendance, but Blackboard gives you one. I said letter only, meaning I only wanted to put present or absent. Okay, and it gives you a score. It made up the score. Yeah,
See, I'm in your math class. Like I was there this morning. I'm in your math class, math 112,
yeah,
and like when you post attendance, like it says I have an A. I mean, I do my work well, but yeah, it says I have an A. Like it says like 100% on attendance.
yeah. And that's because you've been there every day. Some people have one student in another class who I don't know how the system screwed her up so badly, but here's what they did. She took my Calculus 2 class in the summer, and she had an incomplete, but she cleared it incomplete. And she went to register for Cal 3. It wouldn't let her register for Cal 3, and that was a Banner problem. And they said they finally got it worked out. The registrar's office had to manually override to get her in the course. So then she got in the course, and then it wouldn't put her in Blackboard. And if she's not in Blackboard, she couldn't get the code to attend the class. Now she did a few other students shared the codes with her, and she was able to get in. But it was just last weekend, this past weekend, that they finally got it straightened out and that she's able to be in Blackboard. So she came on her own code for the first time Monday, yesterday. And I don't know how in between Blackboard and Banner it just screwed up like terrible. It doesn't do that to every student, but it does to some. Uh, for those who have been in my class before, I was just going to talk about this. I do drop at the end of the term your lowest lab score and your lowest test score, chapter test score. Okay? In the old Blackboard, they had a mechanism there that I could exempt a grade, and that's what I did. And that worked fine. When they went to this new Blackboard Ultra, they took away the exemption of a grade. So the only way I had to drop a course was to remove the grade. And then students say, I know I did this lab. Yeah, I know, but that was your low lab score, so I had to take it out. Otherwise, it was going to count it and pull down your average. Well, this time, for some students, it let me take off a lab or a test score, and other students it wouldn't. And no rhyme or reason, none whatsoever. It's just a fluky thing that Blackboard sometimes does and sometimes doesn't. So um, when we first got started on Blackboard Ultra in the spring, it said you want something about running a running average of your score. I said, sure, do it. I thought it wouldn't hurt anything. That screwed up so badly. They had students who had really good scores. They were given D's and F's, and students who hadn't turned in a thing had A's and B's. And it just didn't make any sense. So I took that thing off because Blackboard, I don't know, it's supposed to be a really good package. I don't see it. Okay, so anyway, enough of that. So let's go back to evaluation assessment. Everyone does a research paper. It counts as a test score. I was going through how many labs we're going to do. Up to, but probably not 14 labs. Like I said, I'll drop at least your lowest lab score, and if we have a lot of extra labs, I may drop your two lowest lab scores. Okay? We'll see. I'll determine that when we get closer. Okay? Your labs will be graded. Okay, picture this, folks, and some of you have been in here before. The course is a 4-hour course. 3 hours are basically what they call theory, and 1 hour credit is a 2 hour lab. Okay, it's a 2 to 1 class lab they call it. Some labs like chemistry have a 3 to 1. Others, like your math courses, developmental math, has a 1 to 1. Well, this has, and biology and most of the others have a 2 to 1 ratio. Okay, you go to lab 2 hours, you get 1 hour credit for it. So since it's 4 credit hour course, 3 of those are your theory, one of those is the lab. I count the lab as 1/4 of the score. Okay, so how I accomplish that? I make every lab worth 25 points. So at the end of the term, when I average all your labs together, you'll have a score somewhere between 0 and 25, hopefully closer to 25. Okay, then you have your test. The research paper cannot be dropped. 6 other tests, I will drop the lowest score, whichever your lowest score of those 6 is. If it helps your average, I drop it. Okay, you'll have the final exam, which cannot be dropped. So don't even bother asking, oh, I've made an A on every test. Do I have to take the final? Yes, that's how we measure your overall competency in the course, is your final exam. So everyone takes the final. Okay? So when I average the research paper, your 5 highest test scores, and the final together, then I'll take 75% of that, because they're based on 100, 75% of that, add that to the 25 or so that you got from your lab. There's your final score. Okay, and then if you come out in the 90s, you've got an A, 80s a B, 70s a C, and so on. Don't go down here. All right, let's talk about attendance. And again, I can't get my, there it is. Um, Students are expected to attend all the classes for which you're registered. Okay, and try to be here every day. Every day I'll post Zoom just like I did before for this class. Hopefully the other people will figure out how to get here too. I usually post it the evening before the day the class meets. Okay, so sometime Monday evening, and when I say evening, sometime after say 4 o'clock, I will be posting the Zoom invite for the next day's class on Tuesday and Thursday. Now those poor people on Monday and Wednesday, now that this class is in session, well, Monday I post usually after my Sunday school class is over, because we usually use Zoom for that. Then I'll post that, so usually that's sometime Sunday morning. But on the Wednesday class, I have to wait until this class is over. I don't have to, but I choose to wait until this class is over with, and then I schedule the 3 classes I have on Monday and Wednesday. On Wednesday, okay, so they will have to wait until after 8 o'clock to see when theirs comes up. But they don't use it till the next morning anyway. But that's when it'll be. Okay, so that's when you look for. Don't look for it super early, and it's not the same code every time. Now the reason I do that is a little extra work for me, but the reason I do this, my wife has used Zoom a lot in her work. She's a professor at UAB, and they have meetings and other things with it. And they found out when they use the same code, meeting after meeting after meeting, hackers get into it, and then they do stupid stuff like putting pornography in the background or something like that, which pretty much takes away from the class. Okay, so I post them a new code every class. So look for that sometime after 4 o'clock on Monday and Wednesday. I'll post the things for Tuesday and Thursday classes. Okay, so try to be here every time. If you can't be here, like I say, I do record the classes. This one is recording right now, and then at the end of the day, I will post it on YouTube, but it'll probably be the next morning before I'll be able to move it to the playlist. So don't look for it until say mid-morning the next morning. Okay, you're not going to see it right after class, because it takes a class that goes 4.5 hours is probably going to take at least 2 or 3 hours to upload. And since this ends at 8 o'clock, 2 or 3 hours, I hope to be asleep. Okay, so the next morning I will move it to the playlist, and then at the playlist you can watch it sometime Wednesday or Friday morning or anytime after that. Okay. All right. Then they say all this other stuff. I'm not going to read all this to you. Statement of discrimination and harassment. Now, this makes more sense on campus, but even off campus, we don't tolerate it. We don't want it to happen. I hope it won't happen. If you get the sense that you're being bullied, even online, or harassed or discriminated against in any way whatsoever, please let us know. We will go do whatever it takes to make you feel comfortable, so we want you to learn. And they list all these things that they could be discriminating about, but look, any kind, let us know. Okay? And this is the Alabama Community College System policy number if you want that. Americans with disabilities, this is going to show up a couple of places. This is something that they require us to post. One reason I have on a headset is I'm hard of hearing, and it's hard for me sometimes to hear what you're saying. This helps a lot. My wife got it for me, hoping I wasn't going to talk as loud. I still talk loud. The other reason I have it is this is a computer I got from campus. I had an older computer from the college that was a wonderful old computer, but it died. It died twice. I brought it back to life once. It died again, so I had to finally get rid of it. They provided me this one. What's that again?
Sir, you and me remember that computer very differently.
I did what now?
You and me remember this computer very differently.
Oh, you do. A lot of that problem we had at the beginning was the system, not the computer. But the computer did die on me, and so that's probably what you remember. But it was I can do most of the things I did on that one, but it's a lot harder to do on this one, okay? Or it takes more things, more materials I had to buy. But my wife's rich, so I don't mind about that. Okay, so anyway, um, the I'm hard of hearing, but the other reason I do this new computer, anytime I turned my head, students couldn't hear me. And some of you probably remember that. Uh, Kept saying something to my wife, so she got me the headset so I can turn my head anywhere I want to, and the microphone's right in front of my mouth. So I'm probably coming in too loud. Sorry about that, but that's me. I'm hard of hearing, so I talk too loud. If you have any kind of disability that you need any kind of accommodation, please follow the directions that are in here. They'll show up one other place. I'll point those out to you when we get there. Okay? And then here it comes. This is the student acknowledgement form. Now, what you can do to fulfill that requirement, there is a whole process you can go through, and I pointed that out to you when we were there in Blackboard. You can do if you want to do that, or if you want to just print off this page and sign or your name. If your name is illegible, then print your name as well, and then the date. If you don't want to sign it and you want to just type it in, that's fine too. Send it to me by an email, send it to me by Blackboard messages. We'll talk about that a little bit later, or send it to me through that link that they have in Blackboard. We'll go back to that in a minute. That's the student acknowledgement page. Okay. Do you have any questions on the syllabus right now? Okay. If not, we'll leave the syllabus here. Okay, so I'm going to close this out. And screen sharing has stopped, so what I'll do is go back to, there it is, here. And now I have to move these things. You don't know what I'm talking about probably, but they have this toolbar or taskbar that pops up not in the middle of the screen, but so it blocks a lot of what I'm doing. Here is that thing that you can do, go through course syllabus agreement. And this one says due date December the 31st, 2019. I think that's sort of old, but see, it does say one attempt left. I didn't do this. This is what they use as an illustration. This is mostly for online classes, but you can use it. Here's the next one, and you can go through and do this if you want to, or you can just print it, copy it, take a picture of it. I don't care, but send me some sort of evidence that you have done that last page. Okay? So that's the syllabus. Any question on this course syllabus? Okay. Now, and usually these three dots will enable you to do something. Okay, so I'll let you figure that out if you want to use this mechanism here. So let's leave the syllabus and go to course syllabus agreement. So this is that page maybe that you were talking about, Brianna, maybe, I don't know. I'm going to click on this and see what happens. I don't usually use this. And see, the grading is 0 maximum points. It says 1 attempt. So I don't know what's going on here. You can fill this out if you want to do this. That's perfectly fine. Now that you've read the syllabus, 4 people, like I said. Okay, that may be someone coming back in. Let me see if it's someone coming back in. Nope, just the 9 of us. Let me make sure I've got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, okay. Okay, so if you want to use this page, you can use it. Knock yourself out. Perfectly fine. Okay? If you want to just send me a picture, PDF, Word, I don't care. Send me some type of indication that you've read the syllabus and agree with it. Okay. Any questions on this before we leave it? Okay. We're just making our way through Blackboard now. So that's the course. Now here's the textbook and other required course material. This was in your syllabus. It's also here. Same paragraph, I just copied it. Same thing. So nothing new here, but it's in 2 places. Okay. Now, here's the Americans with Disabilities, ADA information. Now it's the same information but done in a slightly different way. They changed the paragraph things and stuff like this. So they have a little more information here than what they gave us in the syllabus, but pretty much everything here was there too. They just give you a little more information up here. Okay? And documents of a need, that kind of stuff. So there's more on ADA. If you have any disability, please let us know. That's what I was starting to say. I have loss of hearing, so I'm really fairly sensitive to if you have some type of a thing that's going to interfere with your ability to do well in the course. Please bring the documentation to either Dr. Renee Herndon, and she used to be on the Bessemer campus. I imagine she's still there a lot, and Miss Janine McCoy Jones. It used to be McCoy, so maybe she's dropped the Jones part on the Birmingham campus. They left off the parentheses there, but I didn't do this, someone else did. But anyway, there's more information there. So if you need to see them, if you want to call them, if you want to email them, this is rherndon at lawsonstate.edu. This would be J. McCoy, I assume, at lawsonstate.edu. Lots of ways to get there. Okay. So there's Americans with Disabilities. So I think we finished the first navigating the course. Okay. And start here. Okay. Got it done. Now let's go to instructor contact information. Again, there's no icon, so you can't click on this even though it underlines. You have to come over here to the arrow, go click on it, and here I say preferred contact, email at cfowler@lawsonstate.edu, or you can send it by Blackboard messages. I'll show you how to do that in a little bit. And then ask for my virtual office hours. Okay, here they are, folks. Mondays and Wednesdays, 8 to 10. Now, I have a little bit more to say there, but I'll come back to it. Also on Mondays and Wednesdays, 4 to 6 in the afternoon. Tuesday and Thursday, and for those of you like Diana and Brianna and some of the others that are in other classes, this is going to change for you too, because before this week, I didn't have these office hours on Tuesday, Thursday because my Physical Science 1 class started at 1:15. Since this one doesn't start until 3:15, I now have office hours on Tuesday and Thursday, 1 to 3. And then on Friday from 8 to 12. Now, here's the minor issue with this. We are also required to have virtual advising hours. Okay? Now, my virtual advising hours are Monday afternoon from 5 to 6, Wednesday morning from 8 to 9, Wednesday afternoon from 5 to 6, and Friday morning from 8 to 10. Now, so far this term, knock on wood, I've had very, very, very little virtual advising I've had to do. Students aren't signing up, so I'm in the office then. I'm in the office always, okay? But there's where I am. But if you can't get me during these office hours, it may be I'm with a student, okay, doing virtual advising. So that's the only caveat there, or that's one caveat. I just found out today, now some of you know this, some of you don't. I have a mild form of leukemia, okay? And so I see the doctor about once a quarter. Now what that consists of, I go in and have blood work done, and then he and I sit down on a video chat, telemedicine, and we go over what the results were. We had one of those back in June, I guess it was, and he was happy with the counts. They were a little high, but not too bad. I had to go in last Friday for another set of blood work. They do it about every 3 months or so. And this time my white counts were way high. And also drove down some of my red cells and platelets and other things. So he feels like, and I feel like too, I need another treatment. And they're not able to, here's what they say. The nurse said, we can't cure it, but we can treat it. I've had this since 1991. Okay, so I've had this for almost 30 years now. Okay, it's treatable. So far, not curable, but treatable. So, but the councils creep up. They give me a treatment and they fall back down. They call back up. They give me a treatment. They go back down. Okay, so that's how I've been living my life for the last 30 years. Okay. Not quite. For the first 17 years, I didn't need any treatment at all. But since then, I've had treatment since 2008, periodically. I had the last treatment I had was the 1st of January, so I've gone almost a year with no treatment at all. But here I need one again. Okay, the reason to tell you all that. Um, Tomorrow morning, I've got to go in for more blood work because he wants to check and make sure that the markers are still like they used to be. In other words, that he's doing the right treatment for me. And he also is going to check for some certain types of anemia he thinks maybe the CLL is causing. So anyway, I've got to go in the morning. So I may not be here at 8 o'clock tomorrow morning. I'm going to try to go in for the blood work at 7, but sometimes they're not too swift early in the morning, and I've still got to get back home, and so I may not be here by 8. Okay. Also means that coming up, and this is news to me today, I used to always have my treatments on Fridays, but because it's been 10 months since I had my last treatment, more than 10 months, they don't want to give me the treatment full force. They want to do 2 days in a row, 10% one day, 90% the next day. So that means I have to do a Thursday, Friday. Well, this class meets on Thursday, so I'm hoping I can get the treatment done either in the morning or around noon on Thursday, preferably around noon, but I don't want to miss this class, okay, because this is a mini-term class we can't afford to miss. So if it comes down to it, I'll have it done in the morning. But if the treatment doesn't go particularly fast or well or something, I may not be here right at 3:15. I'll get here as soon as I can. I don't know when this will be. It won't be this Thursday. It could be as early as next Thursday, but that's going to do. And then Friday, that's when I'll have the 90%, and that will be knock out just about all my office hours that day. If I know it ahead of time, I'll let you know. So I won't always be available on a Friday, but if I'm not. Also, the last Friday of this month, I'll be taking personal leave because we've got to go to Georgia and take care of some business. Okay. So anyway, there will be occasions when I won't be able to be in the office all those times. All right, so there's that. Here's my contact information. Again, this one does have an icon and it underlines, so you can click on this, and here's what it, well, somewhere It's taking a while to open. La di da. It usually doesn't take this long. I think I must have done too much talking and it was getting ready to shut down. I don't know what's going on here. Does it? Ah, there it is. My name's Charles Fowler. I'm a physical science, physics, and mathematics instructor. I'm also the mathematics department chair. Here's my email address again. It's already shown up at least once. Here's another time. Again, preferred method of contact. I don't know why they have us put so many times. Either by email at that address or Blackboard message, which I'll show you in a little bit. Okay. Here's a way you can schedule one of those virtual advising sessions if you want to click there. The best hours to reach me, here's my preferred office hours, virtual office hours: Monday and Wednesday, 8 to 10 and 4 to 6, Tuesday and Thursday, 1 to 3, most Tuesdays and Thursdays, 1 to 3, and Fridays, 8 to 12, most Fridays, 8 to 12. Understand that some of these hours, Monday afternoon, Wednesday morning, Wednesday afternoon, and Friday morning, I do have some hours set aside for virtual advising if anyone signs up. If they don't sign up, I'm free for office hours. Okay, I didn't do a little video, so you can live without that. Any questions on my contact information? Okay, let's close that one out and let's move on down to, okay, that's it for that one. I'm going to close it. Here's the weekly assignment and activities. Okay, again, there's no icon here, so you have to open it with the down arrow. And when you click there, you'll see every week's come up here. We've only got the first week now, nothing's in the others, so let's click on week 1. This is the most important week. Okay, I'll show you why in a minute. Okay, overview and weekly to-do list. Okay, you can click on that. And here's what it says. Here's what we'll be doing this week if it ever opens. This week we'll review the syllabus. That's what we're doing now. Research paper instructions, we're going to do that in just a little bit. My locator card, we're going to do that in just a little bit. We'll study chapter 1. They may get to that today. If not, we'll get to it on Thursday. That's What is Science? And that's on pages 1 through 19 if you have your book. Hopefully we'll get to do the first lab. It's all ready for you to go. And if we do finish the chapter and the lab this week, I'll post the first test for you. Okay. We'll meet on Tuesday and Thursday from 3:15 till 7:45 in a virtual class via Zoom. So just like on the evening before each class, I'll post on Blackboard announcements a Zoom invite that will enable you to access the class the next day. You will learn what is in the syllabus. That's what we're doing now. What is required for your research paper. We're going to do it in a little bit. How to navigate Blackboard Ultra. That's what we're doing right now. How science is defined. That's chapter 1. What are its components, measurement methods, and the nature of science. Okay? And here are the objectives. Navigate Blackboard Ultra for this course. That's what we're doing now. Identify the key elements of the syllabus. We've already talked about that. Identify what's required in the research paper, coming up really shortly. Identify the key elements of science. That's chapter 1. Hopefully we'll get to it today. The components of science and the principal measurement systems of science. And identify the nature of science and the scientific method. So those are the basic objectives. What your to-do list is for this week will be: review the syllabus, which we have done, but do it yourself. Complete the course syllabus agreement. Okay, you can do that under the Start Here button. You can do it anywhere you can find it. You can take a picture of it and send it as an attachment to an email. You can print it off. You can scan it. You can do whatever you want to. Attach it to a Blackboard message, or you can do it under the Start Here button or the Week 1 button, wherever you want to do that. This assignment is, okay, doing that student course agreement is linked to establishing your attendance in this class. Now I'm preaching to the choir here. Y'all are here. You've already got attendance. I've marked you on my page here. Okay, I'll mark you on Blackboard this evening. you are here. Your attendance is covered. However, they still want you to do, of course, the syllabus agreement page. It's just not as crucial, time sensitive for you as it is for the people who are not here. Okay. Because if you cannot attend either of the virtual classes this week, today or Thursday, you are already here, then failure to complete that assignment will drop you from the course as a non-attending student. And that's why, if you know any of these people, please get in touch with them. Number two, read and review the research paper instructions, which we're going to go over in just a minute, and submit your proposed research paper topic. You don't have to do it this week, but I encourage you to get it done sooner rather than later. We only have 8 weeks, so don't put it off. Choose a topic. Read and study chapter 1 on these pages, like I mentioned here. We'll probably, if not today, next time, complete lab 1, and then if we get the chapter finished and the lab finished, then I'll post the test, you do the test, and turn it in. I always give you at least 1 week to turn in the lab and to take the test. So even if you can't make it one day, you have a week to get it done. Okay. Any question on that? That is the weekly overview. Okay. Okay. And week 1, whatever, to-do list. Okay. No questions? Now, here is the most important one. Instructional materials, lessons, power, blah, blah, blah. I'll tell you why it's so important. Here is the PowerPoints for Chapter 1. We'll probably start it today. We'll probably finish it on Thursday. Okay, recorded lectures. Here is the YouTube video. Here is how you access. All you do is click on this link and it takes you straight to YouTube. Okay, and what you see here in YouTube, I'm going to move y'all out of the way for a moment here. Okay. These are the classes. The last time we had the class, last spring, there's the class like we're having today. I'll name today's class PHS112 Syllabus. Once I load today's class, I'll take this one off. Today's class will load at the bottom. The old ones are at the top. Okay? Now, obviously, in this class, we got through Chapter 1, which I found very unusual. Because here it says Chapter 3 to 4 lab, and then it goes on. So, I think I know what happened. I think there were some classes that we just didn't get to meet, okay, record. And that may have been various issues. I don't know why. So here are the classes that are recorded there. Notice chapters 3 and 4, 4, 6, 8. Where chapters 2 and part of 3, I don't know. So I'm going to move on down. Here they are. Okay. There is sections 1.1 through 2.2. Here is chapter 2.2, 2.2 to 7. Here was that second lab, and we will, I'm going to hopefully improve on that lab this time. And then we go on down, and you see just about every day after a while, we have a lab. Okay. I'm going to move y'all back to the top again. Okay. And then this finishes up. Those first ones I showed you were from the previous time I taught the course. Who was it? Jacob, I think it was saying you had different memories of my old computer. That's when it was breaking down. Well, when it did break down, I couldn't record those days. So that's why I left some of the old stuff there from previous terms. Okay, so that's why you had some at the very beginning and then you picked up here. And this goes into more classes down here. We ended in 6.1 down here. I believe somewhere up here there was chapter 8. Yeah, there's the chapter 8. Whoops, I went too far. So you have to look around and find all this stuff. If something broke down the previous term, if something breaks down this term, anything I don't get to record, I'll leave it up there from a previous term. Okay, so you'll always have just about everything that we do out here. Okay, so when I record this, when I finish recording this evening, I'll load it to YouTube. Then sometime tomorrow morning, I'll put it on the playlist and it will show up down here. It'll say PHS112 Syllabus. That's always what I call the first one, even though we're doing a lot more than the syllabus. We're going over um, Blackboard, we're going over the research paper, we're going over lots of things. Okay, but I'll just put one name there, syllabus. Okay, so there's the YouTube, um, how you get to YouTube. You just click on the link. Okay, I'm going to leave the link and go back to Blackboard. Oh, could y'all see that? I didn't check. Does the screen sharing still work?
Yes, it still works.
Oh, it did. Okay, y'all saw that. I forgot. Sometimes I forget to look. So there's where you have this. Now, why is this the most important one? Because I'm not going to put that link on every week. I'll say under recorded lectures next week and the following week and everyone, I'll see the YouTube. Oops, here comes Rucker. He must have had to go back out and come back in because I already have him present. Don't I? Yes. Okay. I'll say every week, see the YouTube videos playlist link in week one, because for you this is week one. Okay. Instructional videos, I don't have any specifically for this course. If I do come up with some, I'll post them here. Handouts. Now, here is the research paper instructions for the mini-term course. That's what MT stands for. So this isn't quite the same for those who are in full-term courses. It's going to look a little different, but not much. And here's my locator card. So I'm going to pull up each of those separately. So let me pull up the research paper instruction. Okay, there it is. My screen sharing stopped, so let me find my cursor, okay, and go to a new share, and here's the research paper instructions. Y'all can see that now, right? Okay.
Yes.
All right. You get to choose your topic within the scope of the course, okay? Within the scope of the course. It can be a person, a theory, a phenomenon, an application, or any other such topic with which you have an interest within the scope of the course. Or it can be an internet application or demonstration that you find useful to the class. Let's just say we're talking about Ohm's law in the electricity chapter, okay? And everything I say about it, you think, what is he talking about? You read the book and it's blah, blah, blah. But you find some YouTube video or something else out there and you say, oh, that's what they're talking about. Now I understand. You can write on that. So that's what I mean by an internet application or demonstration that you find useful for the class. And that's why I said if you find an instructional video out there that you find so helpful that explains it better than me, that's fine. I'm not embarrassed. I'm retiring, so it doesn't matter. It's not going to hurt my feelings at all. Or better than the book or whatever, then share it, okay? Write your paper on that. Give me the link, and I'll put it out there for anyone to look at. Not your paper, but the link. So anyone can go to that one. So that would work. So now, what do we mean by within the scope of the course? We're covering physics, we're covering chemistry. Okay? Now, within physics, you have motion, you have Newton's laws of motion, you have Galileo's laws of inertia, you have, goodness gracious, I can't think of his name now, that did planetary motion. We have just all kinds of things. That's all with motion. Energy, work, kinetic energy, forms of energy, you know. At least 3 of you are automotive students. Let me give you a couple of examples of things that automotive students have done. I had one write a paper on regenerative braking. and how that's an efficient use of, whereas before braking was done by friction, friction produced heat, the heat was lost. Regenerative braking used the the braking mechanism to turn a generator to recharge a battery. So in a hybrid car or an all electric car, you actually recharge the battery while you were braking. Okay. Another one, years ago, did a paper on the Wankel engine. I don't know if any of you remember the old Mazdas that had the Wankel engine in it, the rotary engines. Okay. New Mazdas don't have those, but the old ones did. So you can find all kinds of things applicable to your interest within the scope of the course. Okay. And so it goes on. So there was energy, heat, and temperature. Okay, that opens up lots of people, lots of illustrations, lots of application. Okay, electricity and magnetism. Oh my goodness, there's just tons of topics there. There's tons of people there. Okay, it's amazing how much is out there. Or chemistry. My goodness, that chapter we're going to run into person after person after person who contributed really big concepts to the whole understanding of how atoms are put together and how we get the periodic table and things like this. So there's tons of topics. You pick something that's of interest to you within the scope of the course and write your paper on that. Okay? Now, what I'd like you to do this week, if possible, is write your name and the topic you've selected on a piece of paper and submit it to me. Now, this can be, if you want to do it on that same thing that you send me with the student course agreement, you can do that. If you want to just type it up and send it to me as a Word document, you can do that. All I need is a paper topic. That's all. Okay? Just a paper topic. You can change it if you find out that topic is not really what you're interested in, or is too broad of a topic or too narrow of a topic. You can't find enough on it, or you find too much on it. You can narrow it, you can broaden it, you can change it. But get me something preferably this week. Okay? That's your other assignment. No points for it, just like the course agreement, but that establishes you've turned in something in the week. Okay? Now, subsequent to this week, you'll be turning in labs every week. You'll be turning in tests a lot of weeks. Okay? You won't be needing to do that other times. But this first week, your course syllabus course agreement, your research paper topic. Okay. Now, how about the topic? You need to find at least one, but two or more are better, outside sources for your paper. Now, this book does a really good job in at least once a chapter focusing on somebody. They call it people behind the science. Okay? And here they happen to choose for chapter 1 a woman I'd never heard of before I taught this course, Frances Bascom. Okay? And they have a blurb. It's a wonderful little blurb. Guess what? That can't be your source for your paper topic. If you want to write on Florence, I said Frances, Florence Bascom, you have to find the source outside your book. Now, this may give you some information where you can go, and sometimes you look at this and you'll see other people here. Emma Curtis Bascom. Oh, wait, I'm sorry, that's her parents. George Huntington Williams. There's several other people here. There's several other issues addressed here. Anything that comes to mind. Okay? We'll be talking about a variety of theories. We'll be talking about a variety of applications. Pick something. The book is a great source for ideas, but it can't be the source for your paper. So use the book to come up with ideas for your paper. Find something you like, and then find your sources, at least one outside source, two or more better, and do that. The sources can be from books, journals, articles, newspaper, magazines, any materials found in the library, any old library, virtual library, wherever. Or, now here I sort of hesitate, any legitimate source found on the internet. Note the word legitimate. In my mind, probably way more than half the stuff on the internet is total garbage. So don't just pick anything off the internet. Make sure it's something legitimate. Okay? The textbook is not an outside source for your paper. It can be a great source for ideas for the paper topic, but not for the paper itself. Okay. Now your paper must be at least one word processed page of text. That means I don't want handwritten. I don't even really want it typed. I want it word processed. Okay. Now I single space these instructions. I want you to double space your paper. So that means, hey, just one word processed page. That's not that long. It's probably not as long as a lot of your English papers. But let me tell you this. What do I mean by one word processed page of text? Let's say that you choose, you don't have to do it, but you choose to have a header and stuff at the top, and then you triple space and you put the title, and then maybe you triple space again and you start typing right here. Okay? Well, one page of text would go to the bottom of this page, and then on a second sheet of paper, come down through all that other stuff and come at least, you can't see it?
It's just like a big white. Oh, I see it. Never mind. I see it now.
Okay. Come down at least this far. So it's going to be at least two pieces of paper. You can't get one page of text is not going to be just one sheet of paper. It's going to be at least two pieces of paper, because wherever you start here, you've got to, on the second page, come down at least that far. A little bit further is better. What I suggest is shoot for between 1 and 2 pages of text. That make sure you get enough. Okay. Now it's double space. I've single spaced this, and I want a standard 12 pitch or 12 point font. I don't want a little 9 point that's hard to read, and I don't want 26 points that 4 words fill up a page. That's not going to work. So keep it standard. You choose whatever font, but don't get too fancy with it. I don't read hieroglyphics. I don't read Old English. I don't want anything that's going to be hard for me to read and grade. I want it simple, clean. Any of these fonts are perfectly fine. I chose Arial. I like Arial, but you could choose any font that's clean and easy to read. Okay? Try to keep the paper less than 2 pages. You don't have to. That's just a suggestion. I don't want it to be an onerous burden on you. Okay? I want it to be something that you learn something from, but short, sweet. Okay, it's not a writing course, it's a physical science course. So I want you to learn some physical science by doing the paper, but I don't want it to be so bad. Now, if you get so fired up about your subject, you can't stop in 2 pages, you're not going to be penalized. Okay, definitely not going to be penalized. Okay, there's no penalty for it being too long, longer than 2 pages. There is a penalty for it being too short. If you don't meet that criteria of being 1 page of text, you're going to lose points. Okay? Now, I say that there's no direct penalty for it being too long. Okay? But there may be an indirect. Now, I've only had this happen a few times. I've taught either at Bessemer State Technical College back before the merger, and here at Lawson State Community College ever since, for at least the last 15 years or so. Um, so I have probably 20 some years of teaching. Not every year at the very beginning did I do this, require papers, but generally I have most of those years. I've usually taught, like this term, I'm teaching 9 classes. One of them's already finished. I've got, no, I guess it's 8 classes. Yeah, I did have 9, but one of them didn't make. So 8 classes. One of them's already finished. I'm teaching 7 right now, 6 full-time classes and 1 mini-term class. Okay, so, and I've done that, maybe not that many, every term, fall, spring, summer. In fact, it used to be we're on the quarter system, it was 4 terms a year. But it wasn't that long that we did that, and I didn't always have papers then. But I've seen an awful lot of papers, okay? I've only had this happen a time or two, that it looked like to me someone decided, well, I'm not going to do all that good of a paper, but I'll make it long and impress them. It won't, okay? And here's why. When I get your paper, I treat it like it's a 100-point paper. Then I start reading it. And as I find errors or things you haven't done correctly or consistently, then you start losing points. So if you give me a sloppy paper that goes on and on and on for 3, 4, 5 pages and it's sloppy and inconsistent, you're going to be losing more and more and more points. Don't do that. Give me a good paper. Then it doesn't matter how many pages you have, it's going to be a good paper. You're going to get a good score. Okay? So don't try to replace quality with quantity. Okay? That's probably more than I need to say about that. You can use any format you want. Most English classes teach MLA. If that's what you're used to, you certainly can use it. A lot of fields use APA, which is American Psychological Association. They came out early on with a really nice, clean, neat format. A lot of other organizations said, hey, I can't beat this. We're going to use APA format. So whatever format you choose, be consistent. Okay? I'll give you the one example where I've seen probably not often, but a few times. Let's say you're referencing a source here. Let's say you're referencing two sources, and they're both from books or journals or articles, but they're from the same type of thing, but they're different sources. And I've seen it done that here when they make the first reference to the first one, they'll open a parenthesis, put the author's last name, comma, year of publication, close it off and go on. But then down here when they do the same type of a reference, they'll open the parentheses, give the title of the article, comma, page number. Hey, that's not consistent. Well, I think I know what happened. This paper that you got used up here used a format, you copied their format, and then this one down here used a different format and you copied their format. You choose your format and then be consistent with how you use it. Another example is if you start, say, indenting paragraphs, indent them all. If you block them all. I've seen so many times where students start off indenting and then go to blocking and then go back to indent, or they indent here, but they indent here, different places. That's not consistent. I've also seen them change font in the middle of a paragraph, sometimes in the middle of a sentence. That doesn't make any sense. Now, using italics to emphasize something, that makes sense. But changing fonts in the middle of a paper does not make sense. You'll lose points for that. Okay? Content also, oh yeah. Please, just about all your word processing packages have spell check on it. Use it. I've been reading a lot of papers from that first mini-term class, and there's been a couple of them I know, without a shadow of a doubt, did not use spell check. And a few more, I am absolutely certain they did not use grammar check. Please use whatever you can. If you're in an English class now and you have that whatever package they have that you can feed a paper through and see if it can find any errors, use it. I'm not, I mean, I want to see a good paper. Use good proofreading, okay? You can even have someone else proof it for you just to see if they catch something you don't catch. Another good idea about proofreading is after you finish a paper, I remember my senior high school English teacher used this term. She said, let it rest. Set it aside for a few days, pick it up. She said, with fresh eyes, read it. If there's something you can't understand, the odds are she said, I won't understand it either, and that's the same with me. So that's use good proofreading. Content also matters. So if you have inconsistencies in your content, you'll lose points for those. I've had some people write on, say, Isaac Newton lots of times, and they'll give the year that he did something as 1940 something another, and I know, nope, that was 1490 something he did that. They just got their dates crossed up. Hey, that's an error. That's really inconsistent. Okay, so be sure you check for content. I've had it not in this course, but a lot of things on, say, the Pythagorean theorem, and they state it wrong. I know what these things are. I'll be able to tell if you're giving it to me incorrectly. Now, the paper is technically not due until the last day of class, before the final exam. Not the last day of finals, but the last day of class before the final exams. That's that Tuesday, the last week of class. Okay? Because your final exams are going to be turned in on Thursday. So that Tuesday. Do not wait until the end of the class. Start working on it now. That's why I want you to give me a paper topic right away so you can start thinking about it. Start working on it. Like I said, I've done this for many, many, many years, for many, many, many classes, for many, 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 many students. And here's the trend I've always noted. Usually, now this is always the case, but usually the papers that come in early in the terms are great papers. And then as the term rolls on, the quality, it goes up and down some with various classes, but generally the trend is downhill. Those that I've gotten at the end of the term are sometimes my very worst papers. Why? Because they put it off till the end. Oh no, I got to get that done. Type it up, turn it in, forget, not read it, not proof it. You do a lousy job. You get a lousy score. Now, I've had some real dogs at the beginning of the term. I've had some great papers at the end of the term. But the general trend is downhill. Get started on it early so you have more time than you ever will at the end of the term. Okay? You have more time now than you will have then, I guarantee you. You'll have more projects, quizzes, tests. Any of you who are in the last class, how many of you, some of you were always turning everything in on time, but how many of you were turning in 2 or 3 labs that last week, because you just had put them off a little longer. So please get it done early, okay? Now, you will lose points if it's submitted after the last day of class. Not the last day of finals, but the last day of class, okay? That's the stick. Here's the carrot. If you submit your paper this month, the month of October, you get 2 bonus points added to your score. If you turn it in the month of November, you get 1 bonus point added. If you turn it in the month of December, you just get your score. If you turn it in after that last day of class, you start losing points. So please get it done early. Now, here's one thing I require that a lot of other instructors do not. When you submit your paper, please attach a single page from one of your sources. So let's say you had 3 sources. Pick a source, any source, I don't care which one. Then get me a single page. I don't want the whole source, just a single page from that source. Okay? Now, if you did your paper based on that YouTube video you watched and it doesn't really have a print material, then the link from that computer application will be enough. Okay? But if you did get it from a source, which most of you I think will, most of the time that's what people use, print me or copy me a page from a single page from one of your sources. Any questions about these instructions? Any whatsoever? I used to have here my room numbers and all like that. I'm here at home. That's the way to get in touch with me. Any questions? All right. There's a research paper. Okay. Now I showed you because I already had it loaded, but this is where you will find it in Blackboard. Now I have to move this thing again. You can't see it, but it's a pain in the neck because it blocks a huge, not a huge portion, but a portion of my screen, so I can't see. There's the research paper instructions. Okay, now again, you put your thing over it, it doesn't underline. There is an icon, but it doesn't underline. So you have to come over here, click on the 3 dots. It says downloads, click on that. You'll see it downloading over here in the lower left corner. When it finishes downloading, click on it, it opens up. Okay? That's how you get the very thing I just talked about there. Now let's go to my locator card. And that basically is just giving my office hours all over again. Okay, well, why didn't it? Got big and then it disappeared. Okay, let me do a new share with it right there. Now this just lines up everything of where I am when I am. Here's my name again. I'm in the math department, though this is natural sciences. This is a second mini-term course. This is my second mini-term office hours. Um, Fall 2020. My last one. Okay? Okay. I'm usually up here in the office at or very close to 8 o'clock every morning, Monday through Friday. Okay? For instance, tomorrow morning, I have to go get a blood draw. So I may or may not get here by 8 o'clock tomorrow morning. Other times, there may be something come up that I'm here, but maybe not right in the office. Okay? Now, and also remember, on Wednesday morning and Friday morning, I may be doing advising from 8 to 9 o'clock. Okay? No, 8 to 9 on Wednesday, 8 to 10 on Friday. Okay. Now, on Mondays, Wednesdays, I'm office and advising from 8 until 10. At 10 o'clock, I got a Calculus 2 class. That goes until 11:40. Then I have half of my lunch and then a Calculus 3 class. The other half of my lunch, then I have differential equations class, and then I'm off through teaching at 3:45. So I'm office advising from 4 until 6 o'clock when I'm supposedly off. Okay, but I'm here. I'm usually up here working in the office until close to 10 o'clock just about every night. I'll go down and eat supper, come back up. Okay, Tuesday and Thursday, they're a little bit busier days. I'm in the office from 8 to 8:30, okay, pretty much. And then my pre-calculus algebra class is 8:30 to 9:45. Pre-calculus trig is 10 to 11:15. Linear algebra is from 11:30 until 12:45. Then my lunch is 12:45 until 1:45. I'm back here in the office or advising, but I don't have an hour schedule. But if anyone calls, I'll do. And that's from 1:45 until 3:15. And then here in the office for this class from 3:15 until 5:45. At 5:45 we start the lab and it goes until 7:45. Now, will it go till 7:45 every day? Probably not. Especially on those days we do have a lab. When we're finished with the lab, you get to go home. Okay, or you're already at home. But we end the session. But I stay online as long as you have any questions. But when everybody's satisfied all their questions and you're through, then I'll let you go. Today we'll probably be here until 7:45 because we're not going to have a lab today. We'll probably be in chapter 1 by then. Wednesday, just like Monday. Okay. Thursday, just like Tuesday. Friday, technically, let me scoot y'all down a little bit so I can get to my thing. Sorry, my dog's barking if y'all are hearing that. Okay, Friday, I'm in the office from 8 until noon. Okay, supposed to be off at noon. Most of the time, I'm not. I'm still here. Now, they love calling meetings on Fridays. They don't do it as much virtually, but they used to do it a lot when we were on campus. They still do it some. Sometimes I may have to call a meeting for my department or something like that because I am the math department chair. Okay? Um, Remember, probably next Friday, I don't know for sure, but probably next Friday, more than likely I'm going to have a treatment, so I'll be out of the office all Friday. Usually those treatments start fairly early in the morning and they go to sometime in the afternoon. Okay? Can't help it. It could be on Thursday. Now, those who are in my Math 112 class, like Diana, I believe is, I don't know if anyone's in my 113 class. I can't think that they are. And even my 237. I may be out Thursday morning if they do the 10% one day and 90% the next day. I hope to be back for this class at 3:15. If I'm not, as soon as I get here, we'll have class. So don't leave home without me. I'll let you know more Thursday or Monday or Tuesday. Okay. Now, also at the end of the month, that last Friday, I'm going to have to take off my 4 hours this on Friday because we've got to go over to Georgia and take care of some business there. So I know I'll be gone that Friday morning. Uh, so any question? And on that next Monday, we'll be driving back from Georgia. I hope to be back by 10 o'clock that morning. So I may be missing some of those hours also. Any questions? Okay, there's my locator card. It'll be out here on the first week. Okay. And now I got to move all this stuff again. This is such a pain in the neck because this, you can't see it, but this taskbar here blocks so much of my view.
I'll be by there when I get out of class.
Okay, your microphone's on. Okay. All right. Now, these handouts here, in subsequent weeks, weeks 2 through 8, it'll say, under handouts, it'll say, please see week 1, or the research paper instructions and locator card links given in week 1. Okay, I don't post these every time, but I'll refer to this week, just like I'll refer to the YouTube videos. And all the others I'll see week 1. Now, here's the lab. Hopefully we'll get to this by Thursday. And this is the simulation. You may or may not be able to open it, but I'll go through what you might need to do to try to open it. Here is the Word document that I typed up last night that's going to go along with the simulations here. So by Thursday, good idea to print this, or if you don't want to print it, when you are doing the lab, write down the information or type in the information when I'm doing it and get me the lab. Okay? So every week you'll have 1 or 2 labs given. I don't think we'll do more than 1 this week. Now, other material. This is the library something another for physical sciences. Okay? If you need this and want to have it, they sent this link to me. I put it out here. Again, how you open it, it doesn't underline, even though there's an icon there. You have to come over here, click on the 3 dots. It'll say download. When you click on that, it downloads over here and you get to see it. It tells about the library services, I think is what that means, for physical science. And it gives the librarian who's in charge of that, and she'll do whatever she can to help you. So if she can help you find sources for your paper, whatever it takes, she will help you. And I just got this last week or so, so I posted it here. For those who are in the 111 class, I posted it on that week 8 because that's when I got it. Okay, I didn't have it before that. Any question on instructional materials? That's what we've been looking at, instructional materials. That includes your PowerPoints, the videos, handouts, and so forth. In subsequent weeks, it'll refer back to week 1, refer back to week 1, refer back to week 1. There'll be new labs every week, but I'll probably refer this back to week 1. Okay, so that's why I said this is the important one. Okay, now, this week 1 discussion, this is mostly here for online courses, not for virtual courses, because they have discussion groups and things like that. We don't. However, if there's something that comes up in class that you would like to dig into a little bit further and would like to have a discussion on, let me know what it is. I'll put it out here as a discussion, and then y'all can go back and forth. I'll involved in stuff like this. I'll be glad to do it. I'll have it out here every week. If we don't use it in week 1, I'll delete it, but it'll be there in week 2. Okay, and if we don't use it in every week, we'll have one. Here's the lab. Now here I do want to show you this. This is a fluke of this silly template we have to use in Blackboard now. Okay. Notice here, use this space to build your assignment. I can't. There's supposed to be a little plus sign here that I can click on. I can't click on anything here and build anything. So I couldn't put your lab here. I'll show you where well, I showed you already. It was there under the materials. Okay? So nothing there. But if you want to submit it through here, you can certainly do that. Okay? I'll go back and show you that again because I did mean to point that out to you. You don't have to submit it here, but if you choose to, you can. Notice here, grading 25 maximum points, no due date, get it into me. I suggest to you try to get it done within a week, but I don't put a due date just in case you need more time. I don't have to go in and extend it. I just put no due date. But please don't wait till the end of the term and turn in all your labs on the same day. I will not appreciate that a lot. Okay, don't do it. Okay, turn them in as we do them. Okay, week one assessment. Okay, again, I'll open this to show you. They didn't put the little plus sign here, so I cannot put your test here. Okay, however, I will, if I give the test this week, if we cover enough material, I give it, I'll change this to read test one. Okay, I won't be able to post it here, but you can post it if you want to. It will be a category of a test and it will have a 100-point maximum. Okay, so you can submit it this way, or you can submit it by email, you can submit it by Blackboard messages, any way you want to submit it. Okay, but I will change that if we get to the test this week. Okay, all right. Not every week we'll have a test because we only have 6 tests in 8 weeks. So there'll be a couple weeks we won't have a test. And this is how you submit an assignment in Blackboard. I left this up here. Most of these things I took off. It's mostly for online classes, but if you want to do it, you can. I don't have anything in there for week 2, so I'm going to come back up here. Now, let's see if someone's trying to come in. I don't think they are. No. Okay. Now, let's go back up here and we'll close out week 1 and we'll close out the weekly activities. And then I just remembered something I forgot to say. I forgot to type in last night. Like I said, it was late. I forgot to give this information here. So I will put it in from now on. I will provide specific directions. And it's what you've already seen under the overview. On the evening before each class, I'll send out through Blackboard Blackboard announcement, a Zoom invite that'll give you the codes and things you need to enable you to access the not online but the virtual class via Zoom. And I'll again mention the days and the times. It's out there in several other places, but I'll do it there. How to access this, I don't have that live instruction, so I'll probably delete this. Exams, that'll only be for the final exam, and I'll show you. I don't think, unless they did something better this time than they did last time, well, I don't even see the final on here. A lot of these things I'll take off. You won't see them because they're hidden from students now. But again, there, I will be able to post the final here because they put the plus sign. That will enable me to do it. But that's at the end of the term, so don't sweat that for now. But I'll put it there. Okay, and that pretty much covers everything in Blackboard. I forgot that I hadn't posted the live meeting information. I'll get that out there, hopefully before Thursday. Okay, now let me move y'all out of the way again. Rucker, you're in the way. Let me show you the last few things about Blackboard. This is where we are now, course content, right there. This is a calendar. Basically, I don't use it. If you want to use it, if you find it useful, use it. This is your discussion stuff. Unless you really want to have a discussion, if you let me know, I'll try to use it. Frankly, I've never used it yet. Here's your grade book. Now you'll see this start filling out as the term goes on, as I start receiving work in, your research paper, your first lab, your first test, second lab, second test, second, third test, third lab, fourth lab, whatever, I'll start filling out the grade book. Okay? Now, some of those things you posted in the weekly things will go straight into the grade book. Okay? When I grade them, they'll go straight in from there. The things you send otherwise, I'll have to grade them and put them in the grade book this way. Here is the messages. Okay? And here, the one horn uh, says, I don't know who he is. I guess that's a he. He's not here today. And he's not on my roll sheet. Okay? No wonder it's not opening. You're not in the course. Okay? I'll email him back or message him back through here, but he's not on my. Does anyone know him? He's not listed here. I don't have a Dewan. I don't have a horn. Okay? But I'll send back and say, look, you're not on the roll yet. Maybe that's why you can't get that. Okay. So anyway, that's where. Now this is where I will send. You know where I'm sending the labs. That's on your course materials every week. This is when I can't open the test, like I showed you I couldn't sometime, I'll put your test. I'll put all the tests here, whether I put them on the other place or not. So some of the tests you'll have in two places, some you'll only have one, but I'll post all the tests here, okay, under messages. The labs I'll just do on the weekly activities, the course information. Now this is analytics. I don't know what that is. I don't use it. Okay. But this is where you send me messages. You can send me your week one agreement. You can do whatever you want to, your labs, your tests, or just messages. You can send them through that envelope there. I will be checking this every week. I'll be checking emails every week. I'll be checking your labs and tests on the weekly activities every week. So send it to me however you want to. All right, so there's messages. Okay, we're back at the, oh, it took me out of everything. Well, I think we were through. Any more questions about Blackboard? I'll be glad to. Oh, let me show you this just in case. Okay, now, I don't know what you get to see and what you don't get to see, but this is where I have to mark attendance. I'll try to do it every evening after the class is over with, and this is where I post the announcements. You see here, I'm going to click on this, and there's the first one is the Physics 112 class. This is my invite to you, and this has everything. If you click on this, you'll get to see it all. Let's see how many people actually looked at it. 11 out of 19 did, and what do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of the 11 are here. I think that's all we've had. So 2 people looked at it and didn't come. Okay. Now I don't know if any of you are interested in the NASA Community College Aerospace Scholars Program. You can click on this and read about it. If you are interested in it, all the information is there. This is something done by NASA recruiting. They asked us to publish it. I published it. I saw one other thing similar to this that came out just in the last couple of days. I haven't had a chance to post that. I'll post that here too. Now when it's over with, I'll take it off. Okay, like this says November the 18th. So after November 18th, I'll take this off. This one I'll take off when I post the next one for Thursday's class. So tomorrow when I post Thursday class, I'll delete this one and post the one for Thursday. Okay, any questions on that? That's where your announcements are. That's where your attendance is. Attendance and announcements. Okay. Now, I think I'll leave this alone for now and see if I can pull up my PowerPoints. There we have it. Any questions on anything before we get started on physical science, actual physical science for today? Okay. I don't know why this is opening. Well, I think I do know. But I can't get to what I need to. Here, I'll try this. Yeah, here we go. Nope. And this is a strange thing. I don't know if it's Zoom. I don't know if it's computer. I don't know what does it, but it's blocking me so I can't click on the slideshow. Okay. And we'll go from current slide. This is where we'll begin. Now, my question to you is, do you need to take a little break? I know I've been sitting and talking for a very long time. Y'all are certainly free to get up and move around, but has anyone been sitting and also listening and you need to take a little break to stretch? This is,
Me.
please? Okay. So I'm going to pause my recording so there won't be dead time here. I'm going to get up, run downstairs, see what the dog's been barking at, and do a couple things like this. I'll try to be back in less than 5 minutes. So y'all try to be back in less than five too. Okay? And we'll get started on chapter one then. Okay? Any questions before I go?
No.
Okay. So here. All right, I'm back. I hope most of you are too. Um, you'll hear me bad mouthing Banner a lot, and you'll hear me bad mouthing Blackboard a lot. You've probably already heard that. But one thing that is a little bit better now that we're on this system than on the previous system. The old system, we had to enter attendance in the course management system. Okay? And, well, that's probably not the right word. The school management system. It was called Alliant. Okay? And in that, we had to enter both the class time and the lab time. So I always used to say, okay, y'all remind me when it's 5:45 because I have to put in attendance for your lab as well. And sometimes I'd forget and have to remember who was here and who wasn't, and it was a pain in the neck. Banner doesn't have that attendance capability. So I thought, yay, we won't have to do attendance anymore. But then they said, but do it in Blackboard. So that's why I showed you that it's there in Blackboard. But it only is every day. It's not class time and lab time. So I only have to enter attendance once. So I've got you. I hope nobody, well, let me see if anyone came up while I was out there. Nope, don't see any new people here. A little bit disappointed only this many people are showing up, but hopefully the others will show up on Thursday. And if they don't, I hope they get the word they're supposed to turn in their um, syllabus agreement page. Okay. Any questions before we get started today? Now I'm going to move y'all again. Jacob, you're in the way again, so let me move you over here. All right.
Just one question.
Yes.
You're recording this, correct?
Yes, I am. I turned it back on when I came back in.
And you're gonna put it on Blackboard.
It will be, I'll put it in YouTube, but then the link to YouTube is in Blackboard under week one instructional materials. That's where that link is, and that'll be there all term. Every week it'll say recorded lectures or whatever, and I'll always say see YouTube video playlist link listed in week one. So go back to week one and you'll be able to access that. And then, like I showed you, um, the um, the stuff is already there from the last time or two that I taught this course. And as I put a new one on, like today's, when it gets loaded, then I'll take off the one that corresponded to last spring or whenever it was. So yeah, there'll always be, just about the whole course will always be out there. And that's in case Screencast-O-Matic craps one day, or Zoom doesn't work, or something else happens, my computer dies. We did this before. That's why some of those are out there from before, because the computers died, okay? And I couldn't record those days. So when that happens, then you'll always have other stuff out there you can go to. It's the same material, just covered under a different time. So this is one of those nebulous little chapters that they put in a lot of science books. I wish they sort of left out and just put the important things wherever they belong. But this chapter is What is Science? Boy, what a dorky sounding title that is. Okay? you could talk forever on it, or you could say it, sum it up in a few quick sentences. They're going to do in between. Okay? I can't get the slide to advance. Here we go. Here's the core concept. If you do have a book, it's on page 1. That same picture you saw here, a close-up shot of that is given in your, this is a close-up shot in your book. It was a more distant one. Um, the caption sort of says, physical science is concerned with your physical surroundings and your concepts and understanding of those surroundings. And this guy flying on a winged um, paraglider, I guess you would call it, he's using science. I guarantee you he used science to develop and build that thing. He used science flying it. He'll use science landing it, hopefully, and it's just all over the place. The sunset in the background, the beautiful sky colors, all have to do with science. Okay, so here's the core concept on that same page, different slide. Science is a way of thinking about and understanding your environment. That's one answer to the question, what is science? Probably not a very satisfying thing. It certainly covers a lot of the basics, but it leaves a lot to be desired as well. So we will go into this. Some other sort of almost snarky definitions, maybe not quite. The search for sense. Yeah, that's understanding your surroundings, making sense out of your surroundings. Finding order out of the surroundings. Yeah, that's saying almost the same things we did before. And other people look at science as tools and rules. And that's a little limited too. Certainly we have tools and certainly we have rules, but there's a lot more to it than that. But those are all different people's answers to what is science. What we're going to do, here's the overview of how we're going to cover this chapter. It's in two parts, not exactly half and half, but two parts. The first part, the bigger part, a quantitative description. In other words, we're going to talk about, okay, and I don't mean this to sound negatively toward anything, but you know, they talk about social sciences and they talk about natural sciences. They talk about biological sciences. They talk about all the different sciences. They even talk about computer science. So a lot of things will put the word science on there. But a lot of times, some of the, and some people use this term, softer sciences are mostly qualitative. They're talking about the ideas, but not much quantitative. Science, as they're talking about here, definitely deals with quantitative descriptions. We describe objects. We describe the properties of those objects. We quantify those objects. We measure those objects. We use various measurement systems to measure those objects. We'll talk about two of these, the major one being standard metric units. Sure, the U.S. doesn't use them too much, but tell me, you automotive students, aren't you GM students or what? Are you still here, automotive students? Hello?
Yes.
Yes. Are you
Yes, sir.
General Motors or Ford or Toyota?
We're GM.
GM, that's what I thought. They're usually the ones that come in the fall. Okay? Now, General Motors, definitely an American company, right? What do you use for your tools? What are the parts on the car? Are they
Sockets and ratchets.
definitely they're metric? Very little what they call U.S. customary, even though it's a U.S. company. Back when I was a young person, just about all the U.S. cars came with U.S. units, quarter inch, 3/4 inch, 5/8, 7/16, whatever. That was what everyone used on all American made cars. When we started importing a lot from Japan and later and off and on some from Europe, they had the metric. So a lot of times shops had to have both sets of tools. Now, I bet you some shops still have both sets of tools. Why? Because some of the older cars, older US cars, have the old US things. But nowadays, because it's such a global market, just about everybody uses metric in automotive, in airplanes, in just about everything, except our mile markers. And when we're talking about things, we still use US customary. Okay, so we'll talk about both of those. We'll talk about the metric prefixes and what we understand from our measurements. Okay, now what they haven't described here are some of the things. We'll get to those under this understanding from the measurements. We'll talk about some very important concepts here. Your lab will come out of this part right here. Okay. Then the latter part is a little bit shorter. It talks about the nature of science, specifically about the scientific method. We'll look at explanations and investigations. We'll look at laws versus principles and how sometimes something they call one thing and sometimes another. Very similar. We'll look at models. We'll look at theories. This is all how the scientific method is put together. So that's the overview of this chapter. Okay, so let's start with the quantitative descriptions. And the first thing listed here, objects and properties. Okay, objects and properties. What are we talking about here? Remember our surroundings. Our surroundings is filled with objects. I'll look out my back window here. I see part of our garage. That's an object. I see our shed where I store some of my tools, the lawnmower, that kind of stuff. That's an object. I see the dog kennel with a dog house in it, and the dog never goes in, but she's too special for that. I see an umbrella. I see chairs. I see trees. I see grass. I see mulch. I see all kinds of things out there. Those are objects, things that can be seen and touched. And not only can we see them and touch them, we can describe them, we can measure them, we can come up with all sorts of information about them. Now, properties. They're the qualities or attributes characteristic of an object. Okay? Our garage roof, that's all I see of the garage right here. It's a very dark colored roof. It's made out of the asphalt shingles. I know that because I've been on it many times. Okay, I can describe that. I can describe the properties of that. It has grit on it. It has a few leaves on it. And sometimes I go out there and blow them off. My wife won't let me do that much more because I'm getting too old and decrepit. But that's another story. The shed out there, I can tell you its color. I can tell you why it's put together because I put it together. The trees, I can describe. We can refer to the properties, the qualities, the attributes of all those objects out there. Okay? Now, in describing them, we make, and this, it looks like they misspelled it. They didn't. These, and I seldom see this word anywhere but in this book. The reference. It sounds like reference, CE, but these are the reference. These are the comparative properties in other more familiar objects. And to me, these are so lame. There are examples here. Sky blue, lemon yellow. Okay, they're referring to some other object that you have a picture of. Now, I look at the sky out there right now. I see a fair number of clouds, but I see some other sky that doesn't have clouds. And since I was born in North Carolina, though I'm not a big UNC fan, I look at that sky and I say that's pretty close to a Carolina blue, okay, because that's a very light blue. This blue that you see right here, that's a little bit darker. I don't know what color I would call that, but it's not what I would call sky blue or Carolina blue, something light colored like that. It's not an aquamarine blue. It's not a super dark blue either, but it is sort of dark. So there are reference. There are much better reference than the ones they mentioned here. We'll get to that later. Here's the problem though. Language can be subjective. Sky blue here in Alabama may be different from sky blue out in Arizona. Why? Because we have a whole lot more moisture in our air, our atmosphere, than they have out there. Their blue is probably a much sharper, crisper blue than what we hardly ever see here. They would never see the sort of muted blue that comes with a lot of water vapor in the air. Okay? So it can be subjective. I may call one thing sky blue, somebody else from another part of the country may call another blue sky blue. So it's subjective. Somewhat ambiguous. What do we mean? Can see a very pale lemon, or I can see a very dark lemon. Some of the sun-kissed lemons from California, they actually add color to them and make it even a yellower lemon than a lemon yellow would be. So yeah, sometimes ambiguous, and oftentimes circular. I'm referring to something, but I'm using the same thing I'm referring to describe it. Okay? That's circular thinking. That's not very scientific. Okay? So we get to quantify properties a lot more detailed than what some of those others. For instance, in measurements. Again, we use quantitative reference, TS. We often call these our units. Okay? Now they do give some dumb examples, and I've given some dumb in class before. What if I wanted to measure the dimensions of this book? Okay? And I don't have anything really good to use as a referent. I don't have a ruler up here, but what I do have is a pen. Okay? And this book is about 1 and maybe a half pen wide, maybe 2 pens long, and maybe just a small fraction of a pen thick. Okay? I could use a pen as my reference. Not a very good referent, but it is a referent because not everyone would have the same size pen. Here I have another pen that's a little bit longer. Okay? So which pen are you using? Not a very good referent. Okay? I know that, for instance, in the old days, they measured, sounds strange, but they measured how tall a horse was by how many hands high. That would be 1 hand, 2 hands, 3 hands, 4 hands. Because most of the time they didn't have a measuring thing. If you're buying a horse, how many hands high were they? I don't know if y'all know who Shaq O'Neal is. He was a basketball player first for LSU and then later for probably several teams, including the LA Lakers. I think he played quite a while in New Orleans as what were they? The New Orleans Jazz before they moved. But anyway, his hands would be way bigger than my hands. So that was my point. Again, that is a referent, how many hands high the horse is, but it's not a very standard referent. Okay. But here are the steps we use in whatever referent or units we're using. We compare the referent unit to the property being described. Okay, if I was talking about the distance from here to Tuscaloosa, I don't think I'd want to measure that in how many hands. It would take me all day and night and probably the next day to do how many hands it was to Tuscaloosa. Not a good reference. Neither would I use how many pen lengths. That would not be a good reference for how far it is from here to Tuscaloosa. Nor was it a particularly good unit for measuring the thickness of the book because it was just a small fraction of that pen, so it wasn't a good referent there either. Okay? So compare the referent unit to the property being described. If I were talking about the distance from here to Tuscaloosa, I'd probably use miles. If I was really big on the metric system, I'd probably use kilometers. Okay? Those would be the appropriate unit to the property being described, the distance from here to Tuscaloosa. I was talking about how thick is this little piece of paper here, a mile would not be a good unit to use. Nowhere close. I'd probably want to get, and some of you are probably familiar with a micrometer that measures how many microns. And a micron is a thousandth of an inch thick that paper was. And that still might be a little big for how thick the paper was. If I was talking about how thick this uh, diskette is, that would be probably a little bit better there. So compare the referent unit to the property being described. Follow a procedure specifying how the comparison is done. Okay, so perhaps I did, oh, here's not a bad referent unit, but it's not a good one either. Here is an almond. Well, that's not very good. I'll eat that one. Okay, there's a better almond. Okay, now let's say, oh, here comes Jacob. He must have had to leave and come back because I'm pretty sure he was already here. Yeah, okay. Let's say we were using this almond to be our referent. Again, not a very good referent because you're tending to eat it. And let's say I was going to talk about the length of that pen in almond lengths. So I would put it at the end of this pen and mark where it went on the pen and then move it up here, and that would be 2 almonds high, 3 almonds high, 4 almonds. Okay, that's how we would do it, end to end to end. Or I could stick a whole bunch of almonds, lay them beside this, and see how many almonds that would be in length there. Not particularly good, but that's how. Follow a procedure specifying how the comparison is done. Count how many of those standard reference units are used to describe the property under consideration. That would be 1, 2, 3, 4, 5, 6, 7, maybe 7 almonds long, that pen. Okay? Now, it's very essential. I'm going to eat this almond. I've handled it. Okay? Now, it's almost supper time. Okay, long time till supper time. It's essential, and this is very essential for you in this course, that when you are measuring something or calculating something, don't just give me a number. If I said this pen was 7 long, wait a minute, 7 what? It's not, well, actually that could be 7 inches maybe. It certainly wouldn't be 7 miles or 7 kilometers. Certainly wouldn't be 7 millimeters, that was very short, or even 7 centimeters. 7 does not tell me how long the pen is. 7 inches or 7 almonds would give me a lot better idea of how long the pen is. So it's essential that when you're doing measurements, quantifying properties, you do a number and a name. Name your referent, your units. Units are important. They're your friends. They'll get you out of a lot of jams. Now, I hope that one day in your future you'll at least be in a position that you could make a $5 billion error. Okay? I hope you don't make one, but it has happened before. And this is a classic example. I'm using the number loosely because I don't know exactly how many it was, but this really did happen. After World War II, in World War II, the Germans had really developed and enhanced missile technology way beyond what anybody else had. Their V-12 missiles they shot from Germany over to England, because England was the one country in Europe, maybe not the only one, but one of the few in Europe that did not get overrun by Germany in World War II. Okay? And boy, did Germany want to get England. But they just couldn't figure out a way under Churchill. England just was refusing. So they developed their missiles that they could fire from Germany over and hit England. And they were doing incredible amount of damage. England couldn't fire any back because they didn't have missiles that would have that range. So after World War II was over, you would think, on the one hand, there might be a big push for less punish these people as much as possible for all the damage they caused. But in reality, what they did, the West, which is mostly the US, Britain, France, mostly, versus the East, Russia, they were all allies against Germany. But as soon as that war was over, in fact, probably before the war was over, they were splitting like crazy. Russia garnered up as many of those German scientists if they could as they could, and England, France, and the U.S. especially gathered as many as they could because they wanted to build their missiles to be bigger and better than even what the Germans had. They wanted the technology. That technically probably was the beginning of what they called the space race. Um, uh, Russia got a lot of German scientists and they built their space program on that. This was also the beginning of the Cold War that we were having with Russia, or at that time called the Soviet Union. Okay? We gathered as many of those German scientists as we could. Von Braun, Oppenheimer, there's just a whole string of them. Actually, Einstein, he was a German scientist. He was a German scientist, but he wasn't one that was supporting the war effort because he was at least part Jewish, I think, and therefore they wouldn't use him. He had fled and come to the U.S. while the war was still underway. But we got many really smart people either during or after the war. Uh, we didn't want to punish them, we wanted to use them. And that started the space race. Well, guess what? Or Soviet Union jumped out to a lead. They got up into space first. They put the man in space first. I think they put monkeys in space first. They put men in orbit first. They got ahead of us. And we were running like crazy trying to catch up. So the federal government developed, and went through a couple of names. Ultimately, it became NASA, National Atmospheric and no, National National Aeronautic and Space Administration. Okay, I was confusing it with NOAA. The National Aeronautic and Space Administration, NASA, had a couple of names before that, but that was what it came out. And they were pouring the money into NASA, and NASA was doing everything they could to develop missiles, missile technology, develop spacecraft, develop environments. I mean, it was all brand new, developing it from scratch. Okay? Now, they jumped off to a big lead. We started trying to play catch up ball, and we did. And Congress poured the money into it. And President Kennedy at the time said, in a decade, we're going to land a person on the moon. Now, that was really out of the question. Okay? We were nowhere close 10 years before that to do that. But within that decade, NASA had put together enough of a program that they were able to launch the Apollo missions. Now, it wasn't easy, and it surely wasn't cheap. Okay? In fact, the very first Apollo spacecraft that they were going to launch, the three astronauts were in the spacecraft practicing, not planning to even leave the ground. They were just in there to learn the instruments and stuff like this. 3 or 4 days before launch was to happen, something caught fire, blew up, all three of them were killed. That put a big brakes on the system. If that hadn't happened, we'd have beat that decade by a long shot. But that put a big brake on that. Well, they ultimately did get Apollo to work. It worked quite nicely until a later Apollo mission. They lost control Apollo 13, by the way. They made a movie about that one, and they had to fly back to Earth in the lunar module, which was quite an accomplishment. It wasn't designed to fly alone, but they had some good pilots on board and did it. So it wasn't all success, there were failures too. But the cost, they put no limits on it, hardly any limit. Well, as you may know, the Soviet Union fell apart. And when it fell apart, there went the Soviet space program. Well, without that big competition there, Congress decided, hey, we're spending way too much money on outer space. We don't need to do this anymore. And they started cutting, for the first time ever, NASA's budget. And they said, look, you have all these universities out there. They've got their people hired. You don't have to do it all. Farm some of it out to them. Yeah, pay them some to do it, but it won't cost as much as if you have to do everything yourself. You have the national laboratories out there. Farm some of the stuff out to them. So what they did on the next Mariner mission, that's the mission to Mars, they decided to do it brand new, different. Before this, NASA had done everything. They did the design, they did the construction, they did the planning, they did the testing, they did everything. NASA did it all. Now they started farming this out to different groups. And they broke it down into smaller pieces. And they put it out for bid. And one group was to design the liftoff and what they were going to do in liftoff. And then they were going to hand it off to another group and get us into orbit around the Earth. And then they were going to go around the Earth and slingshot off the Earth and go across space, across the solar system to get to Mars. And then another group was going to take over at Mars and then get us in the Martian orbit and then take all their measurements. Another group was going to do that. So it was all set up, and they didn't know how it was going to work, but it was much cheaper than what NASA could do it themselves because they had other teams using their people, paying their salaries, and they're just paying them for a product. So it was much, much cheaper. But it was still in the billions of dollars. Let's just say $5 billion. Well, they were sort of antsy, but liftoff went just as planned. And then when it came time to turn and get into Earth's orbit, the second team had taken over. Their calculations meshed perfectly, perfect going into Earth orbit. And then when it was time to leave Earth's orbit and take off into space, that team that was in charge of that one, it worked perfectly. They meshed well, took off, headed to Mars. They got to Mars right on schedule, right on the money, and then they went to the next team was to take over and go into Martian orbit. The spacecraft turned and crashed right into the planet. What? $6 billion, $5 billion, whatever it was, down the tubes. They just got a few measurements on the way to a crash. What in the world happened? Team number 4 had sent their data to team number 5. Team number 5 assumed their data were in U.S. customary measurements or metric measurements, or one way. What it turned out to be, someone left off the units. The other team assumed they knew what units they were talking about because that's what units they had been using, and it didn't mesh. It crashed. Now I hope that one day you're in a position that you're high enough in some organization you could make a $6 billion mistake, but I hope you don't, especially not for some reason of using the wrong units. Okay? Units are important. They are your friends. Be kind to them, use them. Never give me a number alone without a unit. Not unless you're giving me, this is number 3, okay? In other words, you're matching something, the answer is number 3. If you're doing a problem, numbers are usually going to be followed with a unit. Okay, that was way too long on that slide, wasn't it? Okay, so let's look at some of the metric systems. By the way, we do have in the text many things. There's a picture of a rock that's there, made up of many different kinds of minerals. If you were trying to describe that mineral, you would talk about color, you talk about size, grain size, shape, angular, whatever. That picture is in your book on page 3. Okay, now we're getting into measurement systems. This is on page 4. Okay, now the measurement systems are based on standardized units, and this is what we're talking about. They were using standardized units for the Martian mission, but they were using different standardized units and it didn't work. What used to be called the English system, and some people still call it the English system, and that was because it was developed mostly in England. Okay, we inherited it from England because many of our people came from England. Okay, the units, many of them were based on human body parts. For instance, an inch is just about your first joint of your thumb. That is a good approximation of an inch. Okay, I think you can easily imagine what a foot is. Okay, it's about the length of a male human foot. Okay, approximately. Of course, if you were Shaquille O'Neal, that's a long foot. Okay. Um, Actually, a yard is the distance approximately from your nose to the tip of your outstretched finger. Okay, that was what they called a yard. I don't know if any of you have ever been in the old style fabric stores where the little old ladies who worked in there, you go in and your mom or your grandmom or your wife or maybe you or somebody went in and needed 5 yards of muslin to do something with. Okay, well, what the old lady in the old days would be 1, 2, 3, 4, 5, and if her arms were sort of short, she gave you a little more. Okay, nowadays they have tables that measure it exactly and they cut it right along those lines. Okay, but in the old days, that's how they did it, a yard at a time. Okay, that was how they measured a yard. Now, other things had different measurements. That's doing it that way, the units are not systematically related to each other. For instance, let's use one of the ones I just talked about. How many inches are in a foot? 12. 12 inches in a foot. How many feet are in a yard? 3. Wait a minute. 12, then 3. How many yards are in a mile? 1,760. What? Where do these numbers come from? Well, different ways they came about getting them. They're not systematically related to each other. Let's go to weight measurements. The smallest unit you usually do in weight is an ounce. How many ounces in a pound? 16. Not 12, 16. Where did that come from? And how many pounds in a ton? 2,000. Well, finally we got a round number, but wow, that's a big jump there. Not at all related to 16. You can do other things like capacity. Okay, how many fluid ounces are in a pint or in a cup? Now, some of you ladies may be able to help me. I think it's 8, isn't it? And how many cups are in a pint? 2. How many pints in a quart? 2. How many quarts in a gallon? 4. Okay. Whoa, there's no consistency here. They're not systematically related, and they're not related among other units. Okay. That's a problem with the English system because it was put together historically in different ways and then sort of meshed together. The metric system, however, and the actual term for it is the SI system. And I don't know if you know what SI stands for. It stands for Système International. I can't pronounce it right. It's French. And I guarantee you this, if you've studied much history, you know that for much of history, whatever England did, France was against. And whatever France did, England was against. They fought and fought and fought. They once had a war, the name of the war was the 100-Year War. Now, whether it actually lasted 100 years, I'm not sure, but it seemed like it did. Okay? They just were at war, not constantly, but they were at war for about 100 years. They were always disagreeing and fussing on things. Well, France was a much bigger country than England was. They had about the same population, maybe, but France had a larger land area. So they had regions that were very different from one another. Where England was fairly small, it's all an island. Yeah, they had Wales, they had Scotland, but they were fairly similar. In France, however, you had Brittany, you had Normandy, you had Alsace-Lorraine, you had the Basque region, you had this, you had the Parisian region, you had all these regions that were very different from one another. And typically they tried to cheat one another. Okay? They all tried to outdo each other, and everybody tried to cheat the Parisians because that's where the capital was. Well, the French system was really falling apart. And France didn't have, they had some wonderful times scientifically, and other ways, aesthetically, their arts, their sciences were some of the best in the world for certain time periods. However, along came, just shortly after our revolution in 1776, the French had their revolution. Now, ours was a bloody revolution. It was not pleasant, but it got over with and it settled out. The French Revolution, though, whoa, it was bad. It was so bloody. Some of the people who were allies at first then turned on each other. And the guillotine, they were chopping off heads right and left. Okay? It was not a pretty picture. It was not done well. But part of that revolution, they decided to standardize their measurement system. So different parts of the country wouldn't be cheating other parts. And that's when they came up with the Système International, the international system, the metric system. Okay, established in 1791, either during or shortly after, maybe around the time of the French Revolution. And they identified six basic units. The first measured length, and their measure for that was the meter, which is the Latin and the French word for to measure. Okay, that was one measure, 1 meter. Now, what they didn't use anybody's body parts or anything else. They took their best understanding of the distance from the North Pole to the equator and did 1/10,000th of that or something, some weird number fraction like that, and said that's a meter, based on nobody's body parts but on the earth where we all lived. Okay? Now, as it turned out, the meter is just a little bit longer than a yard. If your yard is approximately from your nose to your outstretched fingertip, the meter would be from the opposite ear to the outfit. That's approximate. So it's a little bit longer, a little over 2 or 3 inches longer than a yard. So our 100-meter football fields, if that was 100-yard football field, 100-meter soccer field is just a little bit longer, a few yards longer. Okay? Now, for mass, how much of an object it is, they originally, in the original metric system, they came out with the unit of the gram. Now, the gram was a very small mass, very small. So they used 1,000 grams. Now, that's called a kilogram. That's the only one of these basic units that has a metric prefix to it, the kilogram. That's how much mass there is. Now, here's just to give you an example. In the English system, the U.S. customary system, there is no standard measure. Well, there is a standard measure for mass, but no one uses it. I wonder if any of you even know what the unit is. It's a weird sounding unit, and you'll think, ew, really? Really. It's a slug, an SLUG. That's the only unit we have to measure mass in the U.S. customary system. Now, they'll sometimes use pound mass or something like that, but really the unit is a slug. No one uses it. You don't go into the grocery store and say, I'd like 3 slugs of potatoes, please. No, no one. They'd look at you like you were crazy. You'd say how many pounds of potatoes, which is a force measurement, weight measurement, or how many kilograms of potatoes, which is a mass measurement. But we don't have a comparable unit. We do have, no one uses. Time, everybody uses seconds. Same in metric, same in English. And second is another sort of strange one because everything else in the metric system is base 10. Remember in the English system, some were 12, some were 3, some were 16, some were 2000, yeah, all over the place. In the metric system, everything's base 10, except for seconds. How many seconds in a minute? 60. How many minutes in an hour? 60. How many hours in a day? 24. How many days in a year? 365 and a quarter or something like that. Hey, time was already established. They didn't change that. If you wonder where the 60 came from, you have to go back to the ancient Sumerians, Sumerians. They were the predecessors for the Babylonians that you probably have heard of. The Sumerians, brilliant group of people. For some reason, they used the base 6 and 10 system together. Um, Other examples of that in measuring angles, how many, they use the same thing. Seconds in a minute, minutes in a degree. Okay, not hours, but in degrees. It's 60 and 60. And then a full circle is 360, which is 6 times 60. Okay, so that's where that came from. So seconds don't usually fit in metric, but everybody uses them. Now, for fractions of a second, yes, they use milliseconds, microseconds, nanoseconds, or whatever. For things larger, we use minutes, hours, and things like that. For measuring current, we use ampere. Okay? Now, we use ampere in this system too. Why? Because basically the ampere was developed after the metric system was in play, so we all agreed to use the same unit for that. Temperature wise, we use degrees Fahrenheit. You might say they use degrees Celsius. No, you'd be wrong. They use Kelvin, not degrees anything. Kelvin doesn't use a degree symbol. But this a Kelvin degree, a Kelvin unit is the same size as a Celsius degree, but their scales start at different places. Kelvin is absolute temperature scale. For amount of a chemical material you have is a mole. We aren't quite going to get far enough in chemistry to go into what that is, but that's a mole SI system. And for light intensity, that's a candela. We're not going to get into that either. We're not going to do the chapter on light. All the other units derive from these, mostly from the length measurement, the mass measurement, the time measurement, the uh, current measurement. These two, yeah, somewhere in there, but most of what we're going to use come from these. The first the first 3 chapters we cover are mostly going to use these 3: distance, mass, and time. Chapter 4 on temperature and heat and temperature, we're going to use those plus Kelvin. And then in chapter 6, we'll get into ampere, which will then lead to volts and watts and all these other things. And then chapter 8, we would get in, well, chapter 7, we would have probably used candela, but we're not going to do that chapter. And chapter 8 gets us right up to the point of using mole, but we really don't go there. That would be chapters 9, 10, 11, somewhere in there. But all the other units derive from that. Pound comes from a force measurement, a weight measurement, which is a force. In the metric system, that's a Newton. Okay? Current is this, charge is Coulomb. voltage is volts, so and power is watts, okay? So energy would be joules. All these other units are based on these basic units. We'll get to them when we get there, okay? Now, let's talk about the standard metric units for the four fundamental properties. I already mentioned them here, we'll say them again. Length. Now, I said the French originally came up with the idea of some fraction of the distance from the North Pole to the equator. That was really hard to measure because there's no really good flat straight line you can do that with, and it would be a very, very long line. Okay, you have to go through very many different countries, and it's very cold up there at the North Pole, very hot down at the equator. That would be very hard to do. So now they use something, and this seems absolutely ridiculous to me, but the distance that light travels in one 299 ninth thousandths, 299 millionths, 792 thousandths, 458th of a second. Okay, yo, who can do that? But that's the official measure of a meter. Okay, mass, that's reference. This makes a lot more sense to me. A standard metal cylinder that they keep in a hermetically sealed container in another hermetically sealed container in a vault that's temperature controlled, uh, humidity controlled, everywhere controlled vault, and no one ever touches it, because if you touch it you might get some oils or something on it and change its mass. So it's there. They copy it and make other countries will have their standard metal cylinder, and they try to be as precise as possible in copying. That's your kilogram. Time, oh boy, here's another weird one. It's reference to the oscillation of a cesium atom. A cesium atom has a very definite oscillation, and that's how they measure a second. So many million trillions of a cesium atom oscillations. That makes a second. Charge we're going to do in chapter 6, the electricity chapter. All other units, now they did leave off temperature here, we'll hit that in chapter 4. Okay? And all other units, volume, area, forces, momentum, everything else you can imagine is based on basically length, mass, time, possibly temperature, possibly current and charge, voltage, those kind of things. So here is the table. This is in your text. And by the way, before you get to this text, they show a fairly interesting figure 1.4 in your text showing two cities here. They don't say which two cities they are, I don't think. Hypothetical towns. They could be 50 leagues apart. That was a very old measurement. I'm guessing came from Roman times, but I'm not sure. 130 nautical miles apart. That would be measured in the ocean, as opposed to 150 what they call statute miles. That's what we use. And by the way, like I said, our mile, statute mile, is 1,760. I've had the ceiling fan on. I think our AC is kicking in or the sun's going down or something, but it's getting a little chilly, so I'm going to turn that off. Our mile is, as I told you before, 1,760 yards. Well, a nautical mile is exactly 2,000 yards. So a statute mile would be 5,280 feet. That would be, nautical mile would be 6,000 feet. 3 times 2,000 yards, it would be 6,000 feet. So it's a little more standard than the other. So that's called a nautical mile. A Roman mile, which is where we got our mile, but we made it a little bit longer, so we don't have quite as many. That's 150 Roman miles. 12,000 furlongs, they use that in measuring horse races. 12, that's 1,200 furlongs, 12,000 chains, which are used in measuring surveys. They use chains for that, as they do rods, 48,000 rods. There's 4 rods in a chain. And then 452,571 cubits. What is a cubit? If my memory is right, it's the distance approximately, again, English measurement from your elbow to your fingertip. I believe that's what a cubit was. Okay, and that would be 792,000 feet. And remember, a cubit is pretty close to 18 inches. A foot is 12 inches, so that's why it would be more feet. Okay, then the next figure, 1.5, shows a man standing there. The inch was his little thumb joint, his thumb joint. A yard was from his nose to his fingertip. A fathom, that was one they left off before, was basically 2 yards or 6 feet. That's a fathom. They use that sometimes in measuring depth in the ocean. A cubit, yeah, is the elbow to your tip of your finger. I was right on that one. A foot is approximately the length of his foot. And 1,000 double paces, whatever they mean by that, and somebody's standard pace, that's how they come up with a mile. Really bizarre. Okay? Now, the next figure is this table you see here. The SI, meaning System International, or you think metric base units. Base unit for length is a meter. The symbol for meter is a little m, meter. Basic unit for mass, the property of mass, is a kilogram. That's the only one that has a metric prefix. A kg. Gram used to be, for the metric system, the basic unit. When they went to SI units, they did, let's do a bigger one, let's do a kilogram, kg. Time, like we said, was second. That's not very metric or SI in its nature, but it's there. Electric current was the ampere. Now notice here that's a capitalized word. Why? A capitalized letter. Why? It's named after Louis Ampere, who did some of the early work with electric current. They named the unit in his honor. So since it's named after somebody, capital A. Meter not named after anybody. Grams not named after anybody. Seconds not named after anybody. Temperature, Kelvin. Now that wasn't anybody's name per se. That was William Thompson's title. He was a very unusual character in that he was part of the landed gentry in England, the royal almost gentry. He was a Lord Kelvin, right up there just below the monarchy. Lord Kelvin, so they didn't want to name it a Thompson, they named it after his title, Kelvin. Very seldom did those landed gentry people turn out to be very smart. He was an exception. The amount of substance you have is a mole, and why don't they just spell MOLE, but they put MOL as an abbreviation. They couldn't use M because they already used M for meter. And luminous intensity, like I said, is a candela, so they use CD for that. Just a C by itself would be difficult because that is a metric prefix for 100th, centi. Okay, so they use candelo to be a CD. Okay, a capital C is usually used for degrees Celsius. Okay, and there are other uses. Okay, so let's talk about the metric prefixes. We talked about how weird the US system was. Here's how organized the metric system was. Surprised that France came up with it. Okay, they simplified the conversion process that all you do is move a decimal. That's all you have to do. Okay, so let's say we have a meter. That would be from your opposite ear to the tip of your finger approximately. That's not how they determined it, but that's a meter. Split that into 10 even pieces, and that's called a decimeter. Well, what's a tenth of a unit is called a decimal, one decimal place in the unit. So decimeter, 1/10 of a meter. Okay? Take that decimeter and split it into 10 equal pieces, and you have what they call a centimeter. Now, centi means hundredth. Okay? Think about, I don't have one on me, a penny. What do we call that? A cent. Why do we call it a cent? It's a hundredth of a dollar. A centy dollar, we just call it a cent. How many years? How, what do we call 100 years? A century. How many soldiers did a Roman centurion have under his command? Approximately 100. Okay? CENT basically means 100. Usually a hundredth, smaller part, 100th, because it's a 100th of a meter, because it's 10 centimeters make a decimeter and 10 decimeters make a meter, so a centimeter is a hundredth of a meter. Then take that centimeter and split it into 10 equal pieces, and that's a millimeter. Now, if I had a dime, I don't have a dime up here either, that's about the thickness of a millimeter, is one dime thick. So it's pretty small. Okay? So everything uses these approximations. Now, we've been talking in terms of meters, but what if we were talking about in terms of gram? We would talk about a gram, a decigram, a centigram, or a milligram. In fact, a lot of medicines are given in milligrams. Okay? That's how we measure mass. What if we were measuring volume? A liter, a milliliter, a centiliter, a deciliter. Okay? Same type thing. Okay? What if we were measuring newtons of force unit? We could say a newton, a centinewton, or a millinewton. Now, a lot of times we don't use that. We use scientific notation, but you could. Everything in the metric system uses the same prefix. Whereas in the English system, 16 ounces is a pound, 12 inches is a yard. Nothing makes sense. Here, everything is base 10, except, of course, for time. Okay. Now, the other advantage to the metric prefix is it helps you avoid writing very large numbers or very small numbers. So if you were talking about the thickness of that piece of paper, you would give it in millimeters thick. It would be a fraction of a millimeter, but it would be a fairly small fraction. If you tried to use a meter and use a fraction of that, it would be an incredibly small number. Okay? You have to have a lot of decimal before you ever got to the first digit, a lot of zeros in that decimal. Okay? Or going up the other way for larger things, we talk about the distance from here to Tuscaloosa, not in meters, but in kilometers, kilometers, meaning 1,000 meters. So the metric prefixes help you avoid writing very large and very small numbers. Okay? It basically helps out in scientific notation. Now, what they didn't give you in the slide set here are a couple of things. One, they kind of mentioned but passed on through. I'll hold it up because I know probably not all of you have your books yet, but get your books as soon as you can. They'll be very useful in following what's going on. In fact, I'm going to say at the end of every chapter, nothing replaces reading the chapter. And the best idea is to read the chapter before we have class. Then, and even when you're reading it, and if it seems like it's just blah, 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 you're already putting it together in your head, so then when we talk about it, it'll come together better. Okay? I remember that from when I was in college. When I could, I always liked to read the material before we had it in class, even though, especially in calculus, I felt like I was just calling syllables. I didn't even know what the stuff stood for. But then when the professor talked about it, then those concepts started coming together. And I thought, well, I should just wait and see what he says. So I wouldn't read the chapter. Then when he was talking about it, it was blah, blah, blah. I didn't make any sense out of it until I started doing homework and stuff, and then it started coming. So I found that it was always a good idea to read before, listen to him talk about it, and then go back and work on it. It gave you a jump on it. So here's the things that we're talking about when I mentioned volume and area. Area is a length by a length, so that would be some square length, like square meter, square inch, square yards, whatever, square miles even, square kilometers. A volume, however, is a length times a width times a height, and that's a cubic length measurement. A cubic inch, a cubic foot, a cubic yard, a cubic mile, a cubic kilometer, a cubic anything. Okay? Um, Volume is measured in a cubic um, length measurement. Area is measured in a squared length measurement. Hang on to the concepts, they'll help you. Now we have other things like capacities, like quarts, which then can be converted to cubic feet or cubic inches, okay? Or liters, which could be related to cubic meters or cubic kilometers or whatever. Okay, now, before we get to understanding this, when we're still talking about metric, here is a table that's well worth a look. This relates your metric prefixes to what they stand for. Remember, you can substitute any base unit here, not just meter, gram, liter, Newton, ampere, volt, whatever you want to put there. These prefixes mean the same thing. Your basic your basic unit is just one of whatever. Then to get something smaller, we mentioned deci, centi, milli. Those are 1 power of 10 each. After we get the first three, we jump to 3 powers of 10. I don't know if you can read this from where you are. I sure can't read it backwards. After milli, we go to micro. Then we go to, I can't read it backwards. I can't hold it up there forever. But get your book and look at them. They go to, goodness gracious, milli to micro to nano to pico to femto to atto. By the time you get to attometer, for instance, you're talking about a nuclear dimension. Incredibly, incredibly small. A femto might be a molecular dimension or atomic dimension, and I mean they get incredibly, incredibly tiny. Now going up from there, 10 of those would be a deca, as opposed to a tenth would be deci. 10 would be deca. Well, think of this. What do we call 10 years? A decade, a hard C sound. Decade, like deca, whereas a tenth of something would be a decimal or a deci. Okay? Then hecto would be 100, and there's only one real place that I know that really comes into play. In the U.S. customary, used to be called the British system, we measured land masses in terms of acres. How many acres of land? And that was so many rods and furlongs and things like this. It's a weird, good old English measurement. The units don't really match up well, but it's there. Okay? Well, in the metric system, they could go from square meters to square kilometers. They don't usually use the ones in between. A square kilometer is way bigger than an acre, and a square meter is basically, I don't know if you can see it, the width, the area of that door beneath the doorknob to the floor. That would be a square meter approximately. Approximately. Not exact, but approximately. That's way smaller than an acre. Well, the thing closest to an acre was a square hectometer, 100 meters squared, not 1,000 meters squared, but 100 meters squared. Well, a hectometer squared, they kind of melded the syllables together and made it a hectare. And that's what they measure land area with in the metric system is hectare. It's a little bit larger than an acre, but it's on the same general size. Okay, that's the only place I've ever used hecto. And then power of 3 with kilo, kilometer, kilovolt, kilowatt, kilojoules, kilo anything. And then 3 times that, or 3 powers of 10 beyond that is mega, then giga, tera, I don't know if it's not peta or peta, and exo. And now you're talking astronomical units. You're so big. Okay. Now, I just wanted to point a few things out to you with those units. I can't hold this up for long, but I'll try. Notice the thousandths of a unit is a milli. There it is right there. The symbol is M. A thousandth of that is a micro, which starts with M2, but so we've already used little m, so they went to the Greek alphabet, and their M is a mu. That's what that is, a mu. Okay? Now, when you went up to bigger units, to mega, that starts with M. So what did they do? They made that a capital M because it's a bigger unit. And since they started with that, all the units above that are capitalized. Giga would be capital G, tera would be capital T, peta would be capital P, and exo would be capital E. That means you're dealing with really big units, anything above mega. So that's the one place where the prefix is capitalized and it's not named after anybody. Units, when they're named after somebody, they are capitalized. Okay, but the smaller units are all lowercase. Now, one other thing before I go any further here is, and this is one I've sort of alluded to, but you need to understand, is what in the world is that thing? That is a cubic let's see, it's 1 decimeter, no, one, it's 10 centimeters cubed. Okay, where is it? Right there. Where is it? There it is, right there. That's 10 centimeters, which is approximately 4 inches, I believe it is. Approximately 4-inch cube. It's 4 inches by 4 inches by 4 inches. That would be approximately now 64 cubic inches. But it's not exact, that's just approximate. Okay? But that's 10 centimeters each dimension, length, width, and height. So that makes 10 times 10 times 10, that's 1,000 cubic centimeters. 1,000 cubic centimeters, some of you folks that are used to being in metric countries, you probably recognize this. 1,000 cubic centimeters is a liter. Okay? So that's why nowadays when they're talking about engine size, do they still refer to any US made engines in cubic inches? They don't, do they? Does everybody use either cubic centimeters or liters? You automotive guys. Even
engine description.
okay, which do they use? The liters, cubic centimeters, cubic inches, or what? No, in the old days, our American made car was in how many cubic inches it displaced.
I want to say they use inches.
They still do use cubic inches. Okay.
But the customer they use liters.
Yeah, that's what I was thinking. Every car we bought lately, and we don't buy cars lately, we don't buy cars often, The last several have been in how many liters, 1.4 liter or whatever. Okay, well, everything's moving that way. That's what a liter is. 10 centimeters by 10 centimeters by 10 centimeters. So that liter bottle of Coke that you might have, they're usually 2 or 3 liters, that's what you're talking about. Okay? And 1,000 cubic centimeters is 1 liter. Well, guess what a thousandth of a liter is? 1 milliliter. So when you're talking about cubic centimeters or milliliters, you're talking about the same dimension. A cubic centimeter is the same as a milliliter. Okay? In the old days, my mom was a registered nurse, and they always referred to medications in cc's, cubic centimeters. They don't even use that term anymore. Now they refer to them in milliliters, which is the same amount of medicine, but now they use milliliters rather than cubic centimeters. Okay? Now, I guess that's all I'll say now. Later we'll do some things that will be making those kind of conversions. Okay, I think I beat that to death. Let's go on to understandings from measurement. This is on page 7, 1.6 in your text. Now, what do we get from measurements? We get data, information. Now, by the way, folks, data is a plural word. A single piece of information is a datum, D-A-T-U-M. Hardly anyone uses that term anymore. When you're talking about information, you usually have a lot of it. That's plural. That's data. So to use your English properly, you would say the data say this. The data indicate this. It's a plural word. It's not the data says this or the data indicates this. That would be singular. It's the data indicate this without an S on it. Okay. Now, once you have the data, you can compare data. And one way of comparing is by looking at ratios. And frankly, you do this all the time. Okay? How do you measure how fast you're going? Anybody? Distance over time. That's a ratio. The ratio of your distance traveled to the time that it took you to travel there. That's a ratio. Ratio is a division of two entities. Those two happen to be dimensions. So you would see miles per hour, kilometers per hour, feet per second, furlongs per fortnight, whatever you are using, that's what it is, a ratio. Now, quite often the ratios can lead to generalizations that can be very helpful, and we'll talk about some of those coming up, one of them being the density ratio. And that's the one we're going to be focusing on in our lab whenever we get to it, probably on Thursday. Okay? Density ratio. That's the ratio of mass per unit volume. Mass per unit volume. Now, in the U.S. customary system, since we don't have a standard unit that we use for mass, we use weight per unit volume, and that's called a weight density. But most of the time in physics and in chemistry, we talk about mass densities, which is mass per unit volume, ratio of mass per volume, and that would be in kilograms per cubic meter, grams per cubic centimeter. In the U.S. customary weight density ratio, that would be pounds per cubic foot, pounds per cubic yard, ounces per cubic inch, or something like that. That would be your density ratio. That would be weight density. Now, we'll also come along and talk about symbols and equations, and then we'll sort of wrap it up with problem solving made easy, which you'll see in a lot of science books and math books. Same type principle, we'll go a little bit on that. So let's start with data. The first thing mentioned here, data. And here's a block about like the one we were just looking at. Data, what you do is you use your measurements and the information you got from the measurements to describe either the objects, like this cube here. What is the size of the object? What's the mass of the object? What's the weight of the object? Something such as that. That's what your data is used for. It could be used for conditions. What's the temperature of the room? What's the temperature of the oven? What's the temperature of the refrigerator? That describes conditions. Events, okay? Driving the car at 60 miles per hour, okay? That's describing the event. Changes, okay? Um, and that could be a ratio of a slope, say, how much is height changing per lateral distance. Those would have the same dimensions, so those would be a dimensionless quantity. So let's look at the dimensions of a cube. Now, they're not giving us any numbers here, and they're not giving us any units either. They just say a cube whose edge, every edge, because it's a cube, all the edges are the same length. Now this one may not look as long, but that's because you got foreshadowing here. Because you see, you're trying to represent a three-dimensional object on a two-dimensional plane. And you have to do some foreshadowing here. But this length here is the same as that length there, is the same as that length there, is the same as that one, and this one, and that one, and that one. And not only are the lengths the same, with a cube, the angles are all equal too. Every one of those is a 90-degree angle. Even though that may not look like it there, it is. Those are all 90-degree angles. That's what makes a cube a cube. All three dimensions are equal and all the angles are equal. Now, that's a length measurement. The length of that edge, they're going to just call S. Okay? Now, what if you wanted to talk about the area of one of those faces of the cube? Well, that's a length times a length. That would be S times S, which would be S squared. What if you wanted to talk about the area of the entire cube? Well, each one of the faces, because each one of the dimensions is the same, each one of the faces is S squared. And you have one face here in front, one in back. One on the right side, one on the left side, one on the top, and one on the bottom. That's a total of 6 faces, okay? 6 faces. Each one is 1 square inch, or S squared. So now you have 6 S squared is being the area of that cube, okay? Well, what's the volume of the cube? That's the length times the width times the height. Well, this length was S, that length was S, that length was S, so your volume is S cubed. And again, a length measurement would be measured in something like inches or millimeters or feet or yards or miles or kilometers or meters or something like that. An area, either area of one face or the entire cube, would be square inches, square meters, square miles, square centimeters, square millimeters, square feet, square yards, something like that. The volume would be measured in a cubic length, and that would be a cubic inch, cubic mile, cubic meter, cubic centimeter, something such as that. Okay? That's how we use data, say, to measure the cube. Okay? Measures different aspects of the cube with just one measurement. If you know it's a cube, one measurement can tell you all those things. Okay? Now, what if we take some ratios of those measurements? So for instance, a ratio is an analysis through a quotient, meaning a division sense, of two numbers. So what if we're looking at the ratio of the area of a cube to the volume of that cube? Well, let's just take a cube that's 1 inch on a side. We already decided that the area of the entire cube would be 6 square inches. 1 square inch for each face, 6 faces, that's 6 square inches. Okay, the volume of the cube would be 1 inch by 1 inch by 1 inch, which is 1 cubic inch. So the area to volume ratio would be, and this is where I sort of have a problem here, They left off the units, and I don't think they should have. Numerically, it's a 6-to-1 ratio, but with units in there, it would be 6 square inches to 1 cubic inch. So 6 square inches per cubic inch. That would be how I would say it. What if each side, though, was 2 inches? Let's go back here. What if each one of those was 2 inches? Then the area of one face of this would be 2 inches by 2 inches. That would be 4 square inches. Okay? But now you have 6 faces, so that 6 times 4 is 24 square inches. But if each one of those faces was 2 inches, like we assume, that's the volume would be 2 inches by 2 inches by 2 inches. That's 2 by 2 is 4 by 2 again is 8. That would be 8 cubic inches. So if it's a 2-inch cube, which is twice the length of a side of a 1-inch cube, the area has gone up by a factor of 4. The volume went up by a factor of 8, 2 by 2 by 2, but the area to volume ratio, this was 6-to-1, that would be 24 to 8, which would be 3-to-1. So the area to volume ratio is actually decreasing when you get bigger and bigger cubes. So move it up to a 3-inch on each side. Well, 3 by 3 would be 9, so 9 square inches on each face. 6 faces, 9 times 6 is 54 square inches. The total area of that cube, 3-inch cube, but its volume would be 3 inches by 3 inches by 3 inches. 3 by 3 is 9, times 3 is 27. The ratio here has dropped again to only 2 square inches per cubic inch. So you see, if you do this in a graph, this is your 1-inch cube here, this is your 2-inch cube there, and here's your 3-inch cube at the back. Here's your area. It goes up relatively quickly. The volume goes up much sharper, flatter here but sharper there, but the area to volume ratio actually declines. Okay, and it will continue to decline. Now, that's just a generalization of your ratios. So what? What difference does this make? Well, let's think about this. I don't know if any of you remember in the old days, before they had freezers in people's homes, they had the ice house. Every town would have an ice house. Now, it's not these ice houses that you see at some places, at service stations and places like that, that you get whatever ice you want there. But the ice house sold their ice in blocks, big old blocks. Okay? The ice houses today that you see in parking lots of service stations and stuff, usually that's crushed. Well, you know this for a fact. If you put cubes of ice in your tea right after you mix the sugar in and it's still warm, it takes longer for that to cool than it does if you put crushed ice. Okay? Because crushed ice, guess what? Same volume of ice, but has way more surface area, because every piece of that is very much smaller. The area to volume ratio is very much bigger. And crushed ice, you're getting down to fractions of an inch, and this ratio keeps getting greater and greater and greater. So you have a greater surface area to volume ratio in crushed ice than you have with cubed ice. And you know that if you've ever drunk iced tea with cubes in it, takes longer for that to cool than it does if you have the crushed ice. Same volume of ice, but just smaller pieces. Okay? Now, and you see the ice melts by how much surface area it has, because that's where it melts. It's on the surface. So say you had one of those big cubes of ice, cut it in two, and now you've made two new surfaces there, haven't you? You had the original surface plus the on either side. Same volume, but bigger area. And then cut it again and again and again and again and again, chop it up, and you have more and more surface area for the same volume. So the surface area to volume ratio, as you get smaller and smaller pieces of ice, your area to volume ratio goes up. And that's why the crushed ice melts faster. Well, I don't know if you've ever done KP or kitchen police in the Army, which also meant keep peeling. Okay, the typical picture is you're peeling potatoes. Well, believe it or not, large potatoes, it's easier to peel 5 pounds of large potatoes than it is to peel 5 pounds of small potatoes. Because guess what? Same weight, but the large potatoes have fewer potatoes, bigger potatoes, so there's less peeling on them. The larger they are, the smaller the area or peeling to volume ratio is. So the larger the potatoes have a lot less peel, so they're much easier to peel. Okay? Does that make sense? Okay. Let's look at another ratio. This is the one we'll be. Yes, question? Was there a question?
No, I was answering you.
Oh,
I was
okay.
answering you.
All right, good deal. Thanks. Okay. The one we're going to be doing in lab is the density ratio. And like I said before, there are two types of density. There's the mass density, which we'll use most of the time. That's the ratio of mass per unit volume. So that would be kilograms per cubic meter, say. Now, here's an advantage of the density ratio. If you had a pound of copper, okay, let's imagine maybe that copper was in pennies, okay, or that copper was in wire, coils of wire, or that copper was in a cube of copper, or any other form of copper. How would you know that's copper besides looking at it and stuff like this? Well, what you could do was determine the mass of the copper, and the pennies may have one mass. I said before they had the same mass. So what if they were different? Um, the pennies may have one mass. The copper wire may have another mass. The cube of copper may have another mass. The brick of copper may have another mass. The volumes are all different. But if you were to look at the ratio of the mass per volume, if every one of them was copper, it doesn't matter how big or how small that is, the ratio would be the same. The density is an intrinsic property of the material, completely independent of how little you have or how much you have. The density is what matters. Okay? Now, I don't know for certain this happened, but I bet it did. Back in the gold rush, okay? Now, they've had several gold rushes. There was one actually down in Georgia, over in Georgia, in the 1839, when they discovered gold around Dahlonega, Georgia. And they rushed down and everybody started mining for gold. It turned out there was very little gold there. They moved on, okay? But then a decade later, in the 49s, 1849, they discovered out in the San Francisco area, and that's where the big gold rush, and people swarmed out there. Okay, and then sometime later than that, they had the Klondike gold rush. When every one of those, when people were digging and mining and stuff like this, occasionally they'd run into something they thought was gold. It looked like gold, everything seemed like gold. The problem, it wasn't. It was called fool's gold. It was called pyrite. It was the mineral. It's actually a iron sulfide, and it looks just like gold. How did they tell the difference? They determined the density. The density of gold is way larger than the density of pyrite. So they used a given volume of it and measured the mass. If the mass wasn't large enough, that was not gold. Now, the traditional story, and I think probably the basis is true, but it may have been Hollywoodized over time, that one of the greatest, earliest mathematicians, scientists, engineers that the world has ever known was, and this was ancient Greece, 300 BC, maybe even further, way back there, was a guy named Archimedes. Okay? And he lived in this little town, I'm pretty sure it was Syracuse, on a small Greek island somewhere. Okay? And everybody wanted that island. It had a king for that little island, and he would have been overthrown many times over if it weren't for Archimedes. Archimedes was a brilliant engineer, scientist, mathematician. Okay? Now, somebody was trying to butter up his king, the king of Syracuse, I think it was, and they had made him a beautiful, intricate, absolutely gorgeous crown that looked like it was pure gold. It was the perfect color of gold. Everything was there, intricately carved. It was just an amazing uh, work of art. But the king didn't trust this guy who gave it to him because he had always been a rival. So he called in his standard engineer, scientist, mathematician, and said, "Hey, Archimedes, I need to determine if this is really gold. Or is this just gold plated? Is this just gold on top of some cheap metal? Or whatever. Is this really gold?" And Archimedes said, "Oh, we'll give it to me." He pulled out his pocket knife. He said, "No, don't mar it. If it is real, I don't want a thing done to it to damage it. I want it to be pristine, perfect. So no, you can't scratch it and find out that way. I need you to determine it some other way." Well, that was quite a problem. Well, Archimedes got to thinking about it and went about his daily life, and it happened to be back in those days they had what they call the common baths. The Roman baths, this was way before the Greek baths, they had these places that you could go in and bathe because houses didn't have running water. Not everybody lived near a creek or a water pond or something like that, and they were quite often pretty nasty. So these common areas were the common baths. Well, he happened to be there to take his bath, and when he sat down into the tub of water and he watched the water level come up, he said, "Eureka," which means I have it or I've got it. Okay? And he realized he could do that very thing with the crown, measure the mass of the crown, and then sit the crown down into a vat of water, measure how much volume of the water it displaced without damaging the crown, and then he could determine the density, and everyone knew the density of gold. It was an intrinsic property of gold. So if this had any cheap metal under it, in it, or anywhere to deal with it, he would be able to find that out because gold was one of the densest of the materials that you had. So supposedly he got up out of his bath and went running to tell the king, "I have it, Eureka." The old wives' tale is he forgot to put on his clothes. And he went running through the city naked just because he was so excited about solving the problem. One of the original streakers. Never mind. Okay. Now, here is our formula for density. Now, for some reason, and this is very standard, the symbol for density, especially mass density, is rho. That looks like a P. It's not a P. It's the Greek letter for that corresponds to our letter R, and that's rho. Okay, now I can't see it on mine because I've got this thing blocking it, but I'm pretty sure that's what it says there. It's the Greek symbol rho. And the symbol for mass is little m. Now these are not units, okay? Don't confuse symbols or parameters for units. Little m in a unit would be a meter, okay? Or a little m before something else would be a milli something, millimeter, milligram, or something like that. Don't confuse this. This is a symbol of a unit, mass, usually a lowercase. Capital V usually stands for volume. Again, a symbol is not standing for volt. That would be this unit for volt, but that's not this, and actually they do use it as a symbol for voltage as well, but that's a different story. But use capital V. Why don't they use a small lowercase v? Because they've already decided to use that for velocity. So velocity would be a little v, volume would be a capital V. So this is basically a parametric equation, an equation made strictly of letters. Density, mass density is equal to mass per unit volume. Okay, if you put units in there, if you put numbers in there, that might be something like 10 kilograms divided by 100 cubic meters or something like that, or 10 cubic meters or something, and that would give you a density in kilograms per cubic meters. So don't confuse the symbols or the parameter for your units. Units have to have numbers in front of them. These do not have unit numbers in front of them. They represent numbers, but they're not. These are your parameters. So that's your density ratio, your mass density ratio. Now if you had your weight density, they may use the rho sub W, meaning weight density, but that would be W divided by V, weight divided by volume. Okay, that would be the difference there. Now, here are one way to look at things. If you had a block of gold, you'd be a very rich person, okay? This is 19.3 grams per every cubic centimeter. So this is a centimeter this way, a centimeter that way, and a centimeter that way. Gold is very dense, 19.3 grams per cubic centimeter. Iron, which is pretty dense, is less than half of that, 7.9 grams per cubic centimeter. So if that other king or whoever it was trying to butter up Archimedes' king, if he had just an iron crown, intricate but beautiful iron crown, but then plated it with gold, just enough so you couldn't tell, it would not be nearly as dense as a pure gold crown. Okay? If you had water, and by the way here, this is an exact. These are approximate. This is exact. How do I know it's exact? That's how they first defined what a gram was. What the mass of a material was, the unit of a gram. They started off with a dimension, centimeter. And by the way, a centimeter is about the width of your little fingernail. Again, this is using body parts, but that's just approximate. It's a hundredth of a meter, which would be about the width of your little fingernail. So if I had a little cube that was 1 centimeter long, 1 centimeter wide, and 1 centimeter high, that would be a cubic centimeter. If you filled that with water, which is the most common material on the surface of the planet, but it needed to be pure water, they decided to let that be 1 gram of water. That would be the mass of 1 gram. Okay, well obviously a cubic centimeter is a very small volume, so a gram is a very small mass. That's why they went to kilogram for the SI unit, not gram. Okay. If you had a cubic centimeter of air, same size, this gold, iron, water, and air, that's only 13 ten-thousandths of a gram per cubic centimeter. So the greater the density, basically the more mass you have per the same volume, more massive. Okay? And that would just be one representation of that. Now, they do a little, not exactly an example, but they do in your book, as with other ratios, density obtained by dividing one number and unit by another number and unit. Okay? Thus, the density of an object with a volume of 5 cubic centimeters and a mass of 10 grams would be 10, let's go back to our unit here, mass of 10 grams divided by 5 cubic centimeters, that would be 2, but not just the number 2, 2 grams per cubic centimeter. Carry the units with you. Divide the numbers, keep the units. Okay? Now, they do give, let's just see. I don't think they do it here. They gave you 3 or 4 materials there. Here are a few more materials with common densities. If you have a block of something and you determine its density is 19.3, it's going to be gold. No matter how big or how small that piece of gold is, it will always have that density. Iron will always be 7.9 grams per cubic centimeter. Water will always be 1.0 exactly gram per cubic centimeter, and air very small. Here are a few other common materials here. I don't know if you can read this from where you are. Aluminum is 2.70 grams per cubic centimeters. Copper is 8 point, I can't read them all. 8.96 grams per cubic centimeter, which is actually denser than iron. Iron is 7.87. Like I said, these are round offs. These are not exact. That one's exact. These are approximate. 7.87 grams per cubic centimeter. Lead, very, very dense. 11.4 grams per cubic centimeter, but still not as dense as gold. Gold's 19.3 grams per cubic centimeter. Water is exactly 1.00, as many zeros as you want to put there. That's pure water. However, if you're talking about seawater, salt water, that you would find in the Gulf of Mexico, the Atlantic Ocean, or somewhere like that, that's 1.03 grams per cubic centimeter. Why? It has salt, which is denser than water, dissolved in it. So that makes its density a little bit more. Mercury, what a surprise. Mercury is one of the few metals that happens to be a liquid at room temperature. Amazing, but true. It has a density of 13.6 grams per cubic centimeter, which means it's flashing here. Can you hear me now? Okay. I guess something hit this button on my thing and it was flashing. Sorry about that. Where did I lose you? Did you?
You held the book up and you were showing us. You started talking about mercury.
Okay. Uh, Mercury is a liquid at normal temperatures, and it's, I guess the book hit that button when I was picking it up. Its density is what, 13.6 grams per cubic centimeter. Lead only 11 point, what is that, 4 or 9, something like that, grams per cubic centimeter. Lead would actually float in mercury. In a pool of mercury, lead floats. Amazing but true. Iron would float. Gold would not float. Gold would sink because gold is denser than mercury. Gasoline, 0.68 grams per cubic centimeter. That means gasoline floats on top of water. That's when you have and oil does too. When you have an oil spill, it floats on the water, blocks the oxygen. The fish and the other things living under there will then drown, basically, because they don't get enough oxygen. that leads to an idea. This density matters, sharks and cola cans. Um, I think this is a pretty lame one, but it is sort of fun to read about. So that's a concept applied that's in your book just under the density table. There's the concept applied. And right under that is our first example, example 1.1. Now, because I don't know if I'm going to have enough room, maybe I do on this page. Let's try it because our formula is right there and everything. I have a Wacom tablet here and a ionizing pen that I can actually do this here. Two blocks are on a table. Now I can't draw decent tables, but I'll give it a shot. Okay, first I'll draw the top of the table here, something like that. And here's a leg, and there's a leg, and back there's a leg, and back here is a hidden leg. Okay, there's a table. You got two blocks on top of it. Now I sure can't draw a block very good either. Let's do it like this, like this, like this, like this, 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 this. My drawings really stink. Block A has a volume of 30 cubic centimeters. So this is block A, and the volume of block A. Now notice how I name things in ways that I can remember what I'm talking about. The volume of block A is 30.0 cubic centimeters. Good unit for a volume. Length times length times length. Now, you might ask yourself, why did I put a 0.0 there? Well, the book had it, that's one reason. But the real reason is this is precisely 30.0 cubic centimeters. Not just 30, but to the nearest tenth of a cubic centimeter, that's the volume. If you said 30 cubic centimeters, that would indicate just to the nearest cubic centimeter, that would be the volume. This gives you how precise your measurement is. And we talk about that in 3 significant digits. Because every, yuck, I can't erase that. I have a little button on the side of my pen and I accidentally hit it, and that's what made it make it just a mark there. Okay. Significant digits, any non-zero digit is significant, and any zero following a decimal is significant, and any digit in between two significant digits is significant. So this is 3 significant digits. If you just put 30 without the decimal or anything else there, this 0.0, you wouldn't be able to tell if it's just 1 significant digit or 2. Then we'd put a bar over the 0 to let you know that 0 is significant. When it follows a decimal, you don't have to put a bar over it because that makes it significant. Okay, that's just a little thing. It has a mass, so this mass of block A is 81.0 grams.
Are you drawing something on the?
Yeah, can you not read it?
No, I think it went above the screen. I think.
Okay, I'm guessing, are you looking at your phone?
No, I'm looking for my laptop.
Oh, a laptop. Okay, well let me put it somewhere else then. Um, if you're on a phone, yeah, it is going to be hard to read. Let me, it was behind the word density, so let me put it somewhere else. Okay, put it down here. The mass of object A, can you read that better?
Yes.
Is equal to 81.0 grams. Okay. Now you have another block here. This is block B. Now I can't draw blocks very well, so just that table leg isn't long enough, is it? That's better. Okay. Now, block B over here is a bigger block, as we'll see in a minute. Okay. This is block B. and it tells us that the block B has a volume of 50 cubic centimeters. So the volume of block B is 50.0 centimeters, cubic centimeters. And they also tell us the mass of block B is 135 grams. Which of these is denser? Can you tell by looking at them? Certainly block B has more mass, so does that make it denser? Hard to say until you calculate the density. So let's do the density of A would be, from this formula here, the mass of A, which is 81.0 grams, divided by the volume of A, which is 30.0 cubic centimeters. Compare that with the density of B, rho sub B, equal to 135 grams divided by 50.0 cubic centimeters. Now notice it doesn't matter how many decimal points you have, it's how many significant digits. 3 here, 3 there, 3 there, 3 there. All your measurements are at the same precision. So now it may be time to pull out your handy dandy calculators. I use my phone up here. I've had calculators before, but right now I'm using my phone. And got to get to the utilities, which has a calculator in it. And let's do for A, that would be 81. Now on your calculator you don't have to put the 0.0. You can, but the calculator is going to take care of it for you. You're going to divide that by 30. So I'll just do that, and that equals 2.7, but because we do have 3 significant digits, I will write that as 2.70 grams per cubic centimeter. Okay, so let's do the density of B. B is 135 grams divided by 50. I don't need to put the 0.0, but I could if I wanted to. Hit equal, and what do you get? Rho sub B is the same answer, 2.70 grams per cubic centimeter. Now, what does that tell you? These are probably the same material. If you look at the table we just had, what material in that table has a density of 2.70? Aluminum. So the odds are these are both blocks of aluminum. They may look different, they may be slightly different color, they may be anything different about them, but if they have the same density, the odds are they're the same material. So there was example 1.1. Okay, let's move on to 1.2. Does anyone need those calculations there a little bit longer? Okay, let's go to one. Let me erase these, and let's do 1.2. A rock with a volume of 4.50 cubic centimeters. So here we have an old rock here. If I could get my pen to show up, there it is. Let's just say this old rock here, okay? And it has, now, we'll talk about later, how in the world do you determine the volume of that? The volume of that rock is, what did they say? 4.50 cubic centimeters. 4.50 cubic centimeters. Here's probably how they determined that. They filled up a container of water, absolutely full of water, but that container has a bigger volume than the rock has. Okay, and what they do, they have something to catch the water under that container, catch every bit of it, and then very slowly, carefully lower the rock into the container of water till it goes completely submerged, and then measure the volume of the water that came out, sort of like Archimedes did in the bath, and that determines the volume. So that's how they determine the volume of the rock. And they also put it on a scale and found out the mass of the rock was 15.0 grams. Okay, what is the density of the rock? Okay, just like before, where in the world is my pen? There it is. The density of the rock is equal to the mass of the rock divided by the volume of the rock. That would be sure you put the right number on the top, 15.0 grams, that's the mass, divided by the volume, which is 4.50 cubic centimeters, and that would produce 15 divided by 4.5. I bet you it's not aluminum. No, it isn't. It's about, now, this one has decimal numbers after it. 3 significant digits here, 3 significant digits there. Don't put every one of those 3's that shows up on your calculator. Stop at 3. 3.33. Look to the right. The next number is also a 3. That's less than 5, so we drop it. If that number was 5 or more, we would have bumped up that last 3 to be a 4. But it wasn't. It was a 3, so we rounded down. It has units though. Don't forget your units. Grams per cubic centimeter. There's the density of the rock. 3.33 grams per cubic centimeter. Okay. Now, they have another concept supplied here. A dense textbook. What is the density of this book? Okay. Now what I would suggest, don't put it underwater. Don't measure its volume that way. But this book is enough of a rectangular shape, you could measure the length, the width, and the thickness. I would say probably in inches, and that would give you, or centimeters, if you have a ruler that measures in centimeters, do how many centimeters the length is, how many centimeters the width is, how many centimeters the thickness is. Multiply those three together, that gives you the cubic centimeters of the volume of the book, and put it on a scale, measure its mass, put it on a gram scale that measures its mass in how many grams, and then determine the density of the book. It's going to be pretty dense. This one's pretty heavy. Question? What is it? Yes, you could. I would take the saran wrap off. I would measure the mass of it before I wrapped it, and then put saran wrap. If you're really, really sure that saran wrap is not going to leak. If this book cost me, what, a couple $100 or something like that, I'm not going to risk that. I'm going to measure it and see if I can do that. Now, if you could somehow hermetically seal it, yeah, that would be fine. But you see, any sealant is going to add to its volume. Saran wrap would not add much, okay? But it could add just a little bit, or it could have little pockets of air in there that would increase the volume, which wouldn't be the book. So I would say use your best careful measurements and determine the volume that way, because I value the book. Okay, this book sort of likes to do these little things. These are called myths, mistakes, and misunderstanding, and that's usually a little purple block like that. And this is one called tapping a can, and you can read that. To me, that one's not very interesting. Some of them are, some of them are not. Okay, so let's move on from here. How are we doing on time? We go to 7:45, so we only have about 20 minutes left. So let's see what we can do in those 20 minutes. Okay, top of page 10, symbols and equations. Now, we talked about this a little earlier. Symbols represent quantities or measured properties. Remember, little m represented mass. Capital V represented volume. Rho represented mass density. We didn't say what represented weight density. I said usually rho sub W for weight density. Those are symbols. Those are not units, those are symbols. Equations are mathematical relationships between the properties, so therefore we use the symbols, and that's what we use. Rho is equal to m divided by capital V. Density is equal to mass divided by time. And equations has to have an equal sign in it. Has to. Otherwise it's not an equation, it's just an expression. Okay? But an equation has that. That means something's equal to something else. Okay? These describe properties, sometimes like the density equation, tells you exactly what material that is. Other times it just tells you a property of that material. It can define concepts or specify relationships. Now they don't do a lot with it, they just sort of blah 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 with words here. Okay? Now, here's another way that we use math. Okay? We love math, don't we? Say yes. Okay. And that is, okay? That is talking about direct proportionality. And believe it or not, you use this all the time. Okay? Now, you might think I have something special in Tuscaloosa. I don't. It's just I used to work in Bessemer, and that was the next big city on down the road. Not that Bessemer was a big city, but the next one. So I always use Tuscaloosa. But, excuse me. Sorry.
Bless you.
Thank you. I need it. Okay. What a direct proportionality means, basically, if two things are proportional, that means two ratios are equal to each other. But we're not going to talk about that type of proportion now. We're going to talk about direct proportionality. What that means is, let's say we're driving from here to Tuscaloosa. Okay? Now, I would say that the distance you travel is directly proportional to the speed at which you drive. That makes sense, doesn't it? If the time is the same, then the distance is proportional to the speed. Right? Because if you drive faster in a given time, you're going to go further. Okay? Now that's a form of direct proportionality. Now, an inverse proportionality means they're inversely proportional, means they go in opposite direction. So let's do it this way. Let's say the time it takes me to get to Tuscaloosa is inversely proportional to the speed at which I'm driving. If I drive really slowly at a small speed, it's going to take me a long period of time to get there. If I drive really fast, so the speed is a large number, then the time is going to be a very small number, right? Those are inversely proportional. As one goes up, the other goes down. Direct proportionality, as one goes up, the other goes up. As one goes down, the other goes down. That's a direct proportionality. Inverse proportionality, they go in opposite directions. As one goes up, the other goes down. As this one goes down, this one goes up. That's an inverse proportionality. Now, how do we represent those? Well, we can change that proportionality into an equation. Remember, that's what we talked about in the previous slide, was equations. A proportionality is not an equation. It just shows the direction things are going. If we introduce the proportionality constant, that makes it an equation. And here's what we mean by that. Well, let me get into this. Sometimes that's referring to a numerical constant, just a number, a pure number, no units with it. Other times it's referring to a dimensioned numerical constant. Okay? And we'll talk about the difference of that a little bit later. Okay? Now, here is a sample of a direct proportionality. A is proportional to B. That means as B increases, A also increases. Now, why they put them on opposite sides, I don't know. But as B decreases, A also decreases. That's a direct proportionality. Now, this little fish-looking symbol here stands for is proportional to. That means is proportional to. It also looks a lot like the Greek letter alpha, but I don't think it's supposed to be an alpha. It's just a symbol that represents proportionality. Looks a little like a goldfish. I like goldfish. Okay? The crackers you eat anyway. Okay. Now, an inverse proportionality is this way. A is proportional not to B, but to the inverse of B, the multiplicative inverse of B, 1 over B. Now let's think about that for a minute. Let's say B is a number. Make up a number. Give me a number. Any number. Not 1. Not 27. Excellent. Okay? 1 over 27. How would that compare? That's a fraction, 1 over 27. Is that a small amount or a large amount? That's pretty small in my mind. What if that B were a 2? 1 over 2, how would that compare to 1 over 27? Oh, good. Yes, much larger. So as B increases, A decreases because 1 over 27 was much less than 1 over 2. Okay? B was increasing. As B decreases, is going from 27 to 2, A increases big time from 1/27th of a dollar to half a dollar. I'll take a half a dollar anytime. Okay? All right. Now, how you change from a proportionality to an equation, you introduce the proportionality constant. So here's something I'm going to write down. It's not strictly mathematical, you might say, but it is, the meaning is true. You can go from, let's go here, from, where is my pen? Come on, pen, show up. Oh, there it is. Okay. A is proportional to B to saying A is equal to K times B. So in this sense, you can change your proportionality to an equality by introducing a proportionality constant. Okay? That's what the K is called, a proportionality constant. And that's what they did here. You change the proportional symbol to equal K. Okay? Actually, it's A is equal to KB. But that's what happens every time. Even in an inverse proportionality, and they didn't show this one, but it works here too. Let me erase my scratch here and say you could then make this the same as, where is my pen? It's in my hand, but I can't see where it is on the paper. Can you see where it is? There it is. Okay, I got it. You can make this as A is equal to K times 1 over B, which you could also say is equal to K over B. That is another way to express it. Again, the proportionality symbol becomes equal K. That's how you change a proportionality to an equation. Okay, now let me erase my scratch here. And, okay, I guess that was all. Now, in your book, they do a little bit more, and that's why I say reading the book is so important. So get your books as soon as you can and see about reading them. Now, nothing replaces reading the chapter. Let me show you another blurb they have here in your text, and this is on inverse square relationships. Okay, it's one of the most important relationships in science, in nature, is an inverse square relationship. Let's say you had a point of light right here. If you were holding a piece of paper here, a certain distance from that light, then it lights it up pretty well. You double the distance, and now look at what's happened. The same amount of light is now spread over 4 times the area. You doubled the distance, but you quadrupled the intensity. Triple the distance, and now you have 9 times the amount of surface area covered by that same beam of light. So your light intensity is going down by an inverse square law. That's what it's talking about. Now, my wife likes to read in the evening, unfortunately after she goes to bed, with a little nightlight clipped on her book or Kindle or whatever she's reading. Okay? Now, that brightens it up plenty to read. But could she hang that from the ceiling? And we have 10-foot ceilings here. Could she read by that? No way, because the light intensity falls out by the square of the distance. That's an inverse square law. It's decreasing by the square of the distance. So not a direct proportionality, it's a inverse square proportionality, inverse square relationship. Okay. Now, they skip in the slide set this portion, so I'm going to go back to it just for a moment here. Okay. How to solve problems. I do want to do this. We don't have much time left, so I'm going to try to do this quickly. You see it in the book there, how to solve problems. Okay? And it begins at the bottom of this page and continues. You'll see these same type things done in many math books, in many science books. And I'm going to go through. I don't always follow these steps, but I try to do something pretty close to them. And the first thing is, just like I said about the book, read through the problems carefully. I'd say read it a time or two. Make sure you understand all the relationships there. Okay? And then they say, make a list of the variables with their symbols, and they say on the left side of the page. I don't care where you put it. When I was doing my table, okay, and those blocks on the table, I wrote the mass, I wrote the volumes, and I wrote the symbol for density. And I identified them in a way so I knew what I was talking about there. That was the mass of block A. That was the volume of block A. So I made a list. I didn't do it on the left side of the page or something like that. Now, the thing you don't know, quite often I will put a question mark by it. Like, what is the density? Look for the question. That gives you the thing you're looking for. So that they call a step A. They say inspect the list of variables and the unknowns. Identify an equation that expresses that relationship, a relationship between those. And we had mass, we had volume, we were looking for density. Oh, we knew that equation. Density is equal to mass divided by volume. There was our equation using the symbols we had identified, putting them in there. Okay? So they like to write the equation on the right side of the paper. I'll write it anywhere I want to. Okay? I'm sort of stubborn that way. If necessary, solve the equation for the variable in question. The thing for your question mark. Now, what they mean by that, ours worked out really nicely. We were given mass, we were given volume, and density was mass per unit volume, so you just plug it in, you got it done. But what if they had given us density and mass? Then your equation, you're looking for volume, that's the unknown, but it's down here in the denominator. Well, when they say solve for the thing that's unknown, that means multiply both sides by volume. That puts volume times density is equal to mass alone because the volumes cancel out here, and then divide by density, and now you've isolated or solved for the unknown in terms of the things that were known. That's what they mean by solving the equation. They're talking about the literal equation, the equation that's made up strictly of letters. No numbers in there yet. Now, do I always do that? No, sometimes I'll go on and plug in the numbers and solve the equations that way. So either way. Now, if necessary, convert unlike units until they're all the same. Okay? Now, if we had had that problem and it had been, let's do block A. Let me go back and see what it was. Block A had a volume of 30 cubic centimeters and a mass of 81 grams. Block B had a volume of 50 cubic inches and a mass of 135 pounds. Can you compare those? No. You have to make sure you're using the right units, similar units. So convert the unknown units. Convert your inches to centimeters or your centimeters to inches, whichever way you need to go. And several times in this course, I'll show you techniques for doing that. You probably have already hit some of them. If you don't convert the units and you're comparing apples and oranges and they just don't compare. Okay? You won't know which is denser. Okay? Now, at some point now when you've done all that, then put in your numbers. Now sometimes I just jump right in and put in the numbers earlier, but when you put in the numbers, put in the units. You noticed I did that on every one of those. I put the units with them. Units are your friends. They're going to tell you whether you're multiplying or dividing properly. Your units will either cancel out or combine properly. If they don't, you've got something wrong. Okay? And then do the indicated numerical operations. That's what I usually call solving the equation. They meant solving the equation literally, just with the letters, then plugging in the numbers with the right units and solving them numerically. Okay? Now, and this is really important, ask yourself, does this answer make sense? Okay? If it doesn't make sense, there's a real good chance you've done something wrong. I can remember one of my first paid teaching jobs. I was an adjunct math instructor at Jeff State, and I was teaching Math 1090, I believe it was called back then, long, way back. Okay, and we had a problem in the book that said a box of 48 cookies cost $1.39. How much would 3 boxes cost? Now that seemed like a pretty straightforward problem to me, except that some students had it in their head they had to use every number that was given. So they took that 48 cookies, which had nothing to do with the cost, and they either multiplied by it or divided by it. Okay? When they multiplied by it, boy, that was one expensive box of cookies. Okay? 3 boxes of cookies. But when they divided by it, they came out with something less than what it was to begin with, which, hey, I'll show you that any day. No, it just didn't make sense. No, you didn't need the 48 anywhere in the problem, so ask yourself, does this make sense? Should 3 boxes of cookies cost a whole lot less than 1 box? No, that doesn't make sense. I've done something wrong. Or does 3 boxes cost 50 times what the one box? Oh no, I don't want to do that deal either. Okay. So take your time at the end, ask that. And then they say step 8, this is the most ridiculous thing. Draw a box around your answer. Now that is helpful for someone grading it, and it may be helpful for you if you're going to use that answer later on. So that could be the case. Okay, unfortunately, we have run out of time. Okay, um, so we'll begin next time with a little bit more of this type of thing. We may do this little, it's not an example, it says it's an example problem, but it's not listed as an example, but we'll start there on page 12 next time. Okay, so no really any assignment except do your syllabus acknowledgement page however you want to do that. Send it to me by email, send it to me by a Blackboard message, or do that thing in week 1. I don't care. Also, if you can, start looking at possible paper topics. Thumb through the book, thumb through other things, see what interests you. Make sure it has something to do with physical science, especially the physics and chemistry part. And if you can, send me a proposed paper topic. Okay? Now, why I want you to send it to me is it's first come, first serve. If you are the first one that sends me Isaac Newton, you get Isaac Newton. Someone else sends it to me. I said, nope, that's already been taken. Maybe do something else about Isaac Newton, but don't do his life. So maybe do his three principles of motion. Maybe do his universal gravitational. Come up with some other thing. So that's why I suggest you get your topic in early so you get the one you choose. Okay. Any questions? All right. If there's no questions, then I will stop sharing. I'm sick and tired of sharing. And once I've done that, I will also um, end the meeting. Any last thoughts? Any questions? Anything? If you know any of the people who are not here, I never did go through that list. Let me read it real quickly. I said Thomas Abrowski, Gerald Jordan, I don't know who he is. Diana Patino, I do know, and some of you probably know her too. Sharonica Ruffin, I seems like I know that name before, but she hasn't been in the class lately. Leon Whitney was in last summer. Uh, Tobias A. Williams Moss, I don't know him. If you do know him, get in touch with him. And Dreshawn Wilson, I don't know that one either. If you know any of these, let them know. They need to either be in class on Thursday or they better turn in that student syllabus acknowledgement or agreement page. Otherwise, they may get kicked out of the class without any to do. Banner supposedly will do that. Okay, so we're in Banner now. Any questions? Then we'll see you on.
So this correct?
Okay, you
Or
sort of.
this lecture, so I can go back and relook at it.
Okay, yeah. It will be, I'm going to start recording as soon as class is over. It probably won't finish recording until sometime late tonight, so it'll probably be tomorrow morning sometime before it gets on the playlist. It'll be at the bottom of the playlist, and I'll take off the one that was at the top. It'll say PHS 112 Syllabus, though we've covered a lot more than the syllabus. Okay? Does that answer your question?
Thank you.
All righty. Bye bye.
Yeah, I was just making sure this class is getting on there.
Yeah.
Okay.
Okay. Thanks much. Bye bye.